PT slab with which most of the RCC consultants are concerned. In many of your projects, you see that the building is provided with prestressed concrete slabs, beams, transfer girders, and so on. And unfortunately, the current practice is that the prestressed concrete design is done by the contractor. I don't know how this thing has started, but unfortunately, it is the trend. So there is a contractor sitting somewhere who takes the drawing from the consultant, drawing or whatever data is available. Then he decides how he wants to do the pre-stressing of some of the panels of the buildings, maybe flat slab or some beam slab and so on. So he prepares his own model in his software, while the RCC designer prepares a model in his own software. So the data is barely given in terms of the architectural drawing, and then two different people model the same structures, maybe same slab and so on, with two different softwares. They have got their own limitations, the softwares. The person who is making model has his own limitations. And the result of that is they produce design. One by the contractor, his PT designer, and in most of the cases they are very junior people because the softwares are new and the experienced senior people just don't want to learn new softwares, so they just leave it to youngsters. So the youngster takes over and he prepares the model, does the design as per the software and sends it to the RCC designer who doesn't know that software in which the design is done, and then the whole drama starts. So my today's presentation tries to address this particular issue and how the final RCC designer who is responsible, no matter he doesn't design the PT slab, but he is considered as a responsible person in the end. If anything goes wrong, the first call is sent to the RCC designer. So my presentation will cover these topics: introduction, the design as received from PT contractor or the designer, then checking the design, which is the responsibility of the RCC designer, then checking the results of the different load cases which the PT designer has done, and then there is a serious limitation on the design of the PT slab which is produced by the PT designer. That is, he says that he can handle only dead plus live load. So there is a design which is prepared only for dead plus live load, but the real building is subjected to some lateral load, wind load, earthquake loads and so on. So all those horizontal force effect has got to be later on superimposed by the RCC designer. Then we see that there is a serious interaction required between the RCC designer and the PT designer. Then and then only a final design safe from all angles can be produced. So we shall consider the PT designer's working, that he generally uses some software specially written for PT design, either the adapt software which is there in use for quite some time. Then we have the wrapped software. Midas also handles in some way. Presently, SAFE also handles PT design, or the last version of ETABS, that is also capable of handling. But most of the PT designers would prefer their own software, that is specially written software like Midas or Adapt and so on. So PT designers prepares independently a model based on his software. The data is supplied by the RCC designer in terms of an architectural drawing with some data given for loads, because PT designer doesn't know for what the building is being used. So he needs some data in terms of the live load, the floor finish load, the wall load, all sorts of loads. Or if it is a transfer girder, then some reaction coming from the top columns and so on. So all that data is now required to be submitted to the PT designer. So he prepares the data based on, he prepares his model based on the data received, and then he transfers that into his model and prepares a design which is meant to take care of only gravity loads. So there is a design produced only for gravity load, while RCC designer has to cater for lateral load, that is earthquake loads. So he needs to know that what is the design moment he is getting for dead load plus live load plus earthquake load and so on. While PT designer does his design only for dead plus live load. So one should know as to what is the difference in the design produced by PT designer. That is, what kinds of moments are developed under his load combinations, and what is the additional moment which is to be considered for providing some additional reinforcement to cater for lateral load. So the design which is produced by a PT designer has got serious limitations, that he is able to handle only gravity loads. So we say that RCC designer has got a task to understand properly his design, to check whether he has really considered all the data given by him, properly modeled the structure, and then got the design and so on. So now we see that the design required received from the PT designer has got few components or few items to be checked. One, the RC designer has to check carefully the model, the loads applied on the structure, the boundary conditions to be imposed. Then there is a load balance concept, that you can apply a small amount of pre-stress concrete, the rest will be taken care of by non-pre-stress concrete. So there are designers with different concepts. Some will say we will balance 50% of the moment under gravity load, rest will be taken by non-PT steel. Some will have 70% figure, some will have 30% figure. The result of that is, at the tender stage, there is a serious issue that whether you are only considering PT design, then for some contractor the design might appear economical from the point of view only consumption of high strength steel, but it may lead to high amount of non-pre-stress steel. So there is a requirement as to, for comparing the designs, as to how much load balance you are considering for pre-stress concrete, and then you are getting some analysis results. So we need to check whether the analysis result that is produced by a PT designer are generally logically acceptable as a qualitative variation, and also as numbers. There should not be vast difference in the design moments used by a PT designer and the design moment which otherwise an RCC designer would have used for his normal RC design. Okay, so we say that as far as the RC designer is concerned, once he gets the model prepared by PT designer, then he has got a model. For example, on the left side, as you see, that we have got the adapt model for this particular floor prepared by a PT designer, while corresponding to that, an RC designer has already prepared an ETAB model. So there is an ETAB model and there is a adapt model. So we need to compare very carefully, because both the models are prepared from architectural drawing. So we need to check very carefully whether the dimensions are proper, whether properly all the structural members planned by RC designers are accommodated in terms of the columns, the shear walls, the slabs, beams and so on. So all the relevant members, the bare minimum agreement must be there in the two models. After that, we need to consider other parameters like whether the member sizes taken by PT designer and the RC designer are the same, because initially when the RC designer tries to work on that, he tries to design it for RC member, maybe requiring some different dimensions, while later on PT designer, because of his introduction of pre-stress, he might reduce the sizes, and the result of that is there might be a scope for difference or variation in the sizes adopted by PT designer and the RC designer. So if at all you have prepared earlier an ETAB model, you need to check it very carefully whether the same sizes are adopted. Obviously the sizes will be reduced, because that is the reason why you are going for PT design. So as soon as a PT designer finally agrees to a size or accepts a size and models his structure accordingly, we have to see very carefully whether now your ETAB model is in conformity with that. So we need many times a correction in the ETAB model to accommodate the sizes which are taken by the PT designer. Then we need to consider the loads applied on the structure very carefully, because you are giving simply some information to him that floor finish is so much, superimposed load is so much, wall load is so much at these locations, and so on and so forth. The internal, external walls, all sorts of data is given by you. But when he transfers it to his model, then there is a chance of error. As a result, member by member, we need to consider very carefully whether the relevant load is applied or not. So we have to see very carefully whether the floor finish is properly applied at all the locations in the same way, the wall load. So you have to keep the two models side by side and carefully check whether the relevant loads are applied or not. It's a clerical job and it has got to be done. Otherwise, in the end, there may be vast difference in the results produced by the two models. So we see that all types of loads that you are considering has got to be properly compared and agreed upon, that all the loads are properly applied in both the models. Okay. Now once you do that, then the next stage is you have got the members ready, members are in proper place, you have got member sizes okay, you have got the loads on it okay, you have got the material, maybe he might be using M35 concrete, M40 concrete. Oh, you have to also consider your model with that grade of concrete. The column sizes and so on, they are all to be considered. And then you have got the results produced by the two softwares. So you have got one result produced by the ADAPT software and the other result produced by ETAB model. But we have to understand that ADAPT software is going to give you results only for dead plus live, while you are going to get results for all the maybe 50-60 loading combinations that you have in ETABs. So we have to carefully consider the bending moment diagram produced by ADAPT, whether your bending moment diagram qualitatively is of same shape, cantilever like a cantilever, simply supported like a, and so on and so forth. So all sorts of comparison is required to be done. Later on, if you see most of the PT designer, because they have got two ways of resisting the bending moments, the non-PT steel and the pre-stress concrete. Now as a pre-stress contribution, you have very little knowledge because you are not an expert in that. So you have no idea as to how much of pre-stressing force he is applying and what is the contribution to the total moment resistance offered by pre-stress concrete and so on. So generally software like ADAPT and so on, they produce a final figure that you have got some pre-stress force with all the profiles, and then you have got some non-PT steel. With these two together, he produces a result saying that there is so much of the moment resisted by pre-stress concrete, that is pre-stressing force. There is so much moment resisted by non-pre-stress steel, that is the normal steel, and together whatever pre-stressing force he is applying, the cables he is providing, and whatever the non-PT steel he is providing, the two together are capable of resisting this much moment. So we have got this information ready, that though he has considered dead plus live load, but finally he produces a design which is slightly on the safer side. So he has got capacity of the beam to carry moment, which is partly due to pre-stressing cable, partly due to non-PT steel, and there is a capacity. Now we have got ETAB model with all sorts of loading combinations, 50, 60, 100 loading combinations. With all those loading combinations, you can produce design, okay. But that is going to be RC design because you are using RC design option. While he is producing a PT design. The result of that is, now as you have got the design moments and he is giving you the capacity of the PT beam to carry the moment, then we have to compare the two. The maximum moment that you are getting in any beam anywhere, and the capacity of the pre-stressing force and non-PT steel that he is giving. So there is a capacity of the beam and there is a demand of the beam on the beam, that so much moment has got to be resisted. Once you know the two figures, then you are sure whether there is a deficiency in the design produced by a PT designer or not. Once you realize that, oh, there is a deficiency, okay, then you have to provide for that deficiency the additional reinforcement required. Whatever the moment, the balance moment you have to consider with all the load factors and so on. So in the usual way, you have to provide additional reinforcement, because he is giving you not the bending moment alone, but he is giving you a capacity of the beam to carry moment. If he gives only bending moment, then you can only subtract his moment from your design moment and get the balance. But he is not giving only the bending moment, but he is giving you a design, and that design reinforcement and PT has got a capacity. The result of that is you have to compare the capacity of the beam to carry shear, to carry the bending moment, with the demand on the beam to carry moments and shear forces due to various causes or various combinations. So we have to consider this difference very carefully. I am giving you one more example, very small example over here, where we have got a very simple model where the slab has got large span in this area. So a pre-stress concrete option is used. Even in this part also, pre-stress concrete option is used. So we have got the two models. I think this model on the right hand side is not ADAPT model, is an actually ADAPT model, and the left hand side is the ETAB model. So the two models are ready with all the columns, positions, the beams and so on. Then we have got the sizes of the members, so we can compare very critically the sizes of the members in the two models. Then we have got the two models with the slab load. So we have got live load on the slab, the thickness of the slab, everything is there in the model. So we have got the live load on the model to be compared. So ADAPT model shows in some corner some display with the value of the load. You have to compare it very carefully. In most of the cases, the PT designer is very careless about the area on which, or in the area in which there is no pre-stressing done. For example, in this building, in this part of the building, pre-stressing is not done. So he is very careless because he is not concerned with that. He is not going to do any design for that. But if there is a common element, for example, if this beam is there, then this beam takes load from the area which he is pre-stressing and load from the area which he is not pre-stressing. The result of that is, in this part of the area slab, he is not involved in PT design, but he has to take the load. If he is very careless in modeling such kind of items, I have seen many people not modeling that part also. In that case, in the common beam over here, you are able to get a design which is of little use to you, because you have a full set of loads on different areas, while he has completely ignored the some part of the area which is not pre-stressed. So the first thing an RC designer must ensure is that he must insist on the PT designer that the entire floor has got to be modeled and all the loads are to be properly applied in the area where pre-stressing is done and in the area where pre-stressing is not done. In both the areas, the loads have got to be properly applied. Then and then only his design will be of some use to you for further modification. Then there are design concepts involved in pre-stress design, unlike RC design. In RC design, we have got slab design. If you go to safe, then you provide some design strips in the safe, in safe model, and in design strip you can carry out the design per meter. You will be able to provide reinforcement. While for ADAPT or some such software, also they have got design strips. So you have to see very carefully what types of design strips, the location, the width he is providing. The same design strips you have to transfer to your model. So we have got the ADAPT model obtained from the PT designer. He is providing some design strips in X direction, Y direction. For comparison purpose, you have to provide same types of design strips so that your moments can be compared. You have got the design strips in Y direction, the design strips in X direction. You have to prepare your model, ETAB model, to suit his design strips so that you will be able to compare the moments in the design strips later on when you need to compare and get the difference and provide additional reinforcement and so on. Then you have got the bending moment diagram as produced by PT designer for dead plus live case. If he gives you moments for dead plus live plus PT, that will be useful to you only when you are going to consider the next work of providing additional reinforcement. But at the stage of checking, you need to consider firstly whether the bending moment diagram that you are getting in ETABS model and what he is producing in ADAPT model or whatever is software, are they at least qualitatively in agreement? And numerically a little difference here and there may be okay, maybe 5-10%, because the modeling concepts are many times different. The finite elements are of different size. Sometimes in ADAPT they use 3D models, 3D finite element, while ETAB might do only 2D modeling and so on. The result of that is some difference is expected, and with the result we will say that firstly the qualitative agreement must be there between the bending moments or between the moments in both the directions. Once you are satisfied that yes, the moments are generally in agreement as far as the bending moment diagram is concerned, and for peak values you can that 5-10% variation on both sides may be acceptable, because in the end he is going to give you the capacity of the PT beam, and you have got further chance that you have the demand on the given beam and you have the capacity. As a result, you will be able to provide additional reinforcement in that particular case. So we say that this type of checking is absolutely necessary for arriving at a decision that so much additional reinforcement is required. In pre-stress concrete, the effect of pre-stress concrete is felt only for resisting bending moment. When there is a shear force, then we say that for shear force, pre-stress plays very little part. At the most very little, hardly 5-10% increase in the shear strength of concrete is observed, but that is rarely used. So shear design can be totally done by the PT designer, though he might give you some design based on the dead plus live load, but you can produce independent shear design, the stirrups and so on. Based on your design, you can totally ignore his design because it is of no use to you. There is no advantage gained by providing pre-stress concrete in resisting shear and so on. So we see that we need to consider this type of checking for the two models, the model prepared in ADAPT and the model prepared in ETABS. So if this kind of checking is done, then we say that firstly you have got confidence that he is using the same data, same loads, same model, same beam sizes for his design, and accordingly you are assured that whatever modification you do is for the same type of members and so on and so forth. Many PT designers give further data as to the stress variation, the top stress, the bottom stress under different conditions. It is necessary for you to make some efforts to understand what kinds of stress distribution he is displaying, and to make some queries at least whether it is as per the provisions of the IS code and so on, because he might violate some conditions for some purpose or there might be genuine reason for that, but you are finally a signing authority and you are the authority to take the entire responsibility. The result of that is it is very much desirable that you understand what kinds of stresses are produced in the pre-stress concrete behavior, and that is pre-stress concrete application, and you must agree whatever it is. You can take his help to ask him, show what are the permissible stresses and satisfy yourself. Yes, this is the permissible stress, this is the actual stress, and so on and so forth. So we see that we need to consider a very rational approach in checking the design, and my earnest request to all the RC designer is that don't leave this design to PT designer entirely. It is finally your responsibility. You are going to sign it. If there is any problem, you are going to face it. Many PT contractors, they form companies, they do business for few years and then they vanish. We have seen many companies like that. But you are running a company maybe for your whole lifetime, because yours is a professional company for designer. The result of that is you are liable for your entire life for any effect or any defect that might be noticed later on. So my sincere wish is that all the RCC designers should learn how to do the PT design. Like you are doing design and the contractor is constructing it. He is not going to produce design, normal contractor. Why not same thing should happen for PT contractor? Let him use his tools or his technology for construction purpose. For design, you are the designer. I think that approach should be taken by all the RC designers, and I am involved in many of the projects on the side of PT contractor and sometimes on the side of RC designer. So I have seen that a single agency is the best agency. There is no point in having two design agencies, one partly doing work, other partly doing work. It is like tomorrow someone will say, I am an RCC designer specialized only in beam design or column design, somebody else will do. So I think that is not going to work. You have to do the complete design, or at least RC, PT, everything is your jurisdiction. So you must learn and finally produce a design with which you have got full confidence that everything is made as per the codal provisions, and then there is no issue at all. I think that is all right for my first part of the presentation. And as far as the design is concerned, that is all is involved. And as far as the later on the site reports are concerned, I think many times you see that from site you get all sorts of reports about the stressing of the cable. So you have got a big table in which he says that, oh, for this cable number so and so, this was the elongation expected and that is the elongation obtained. And then finally he says that, okay, sir, you certify that. So you don't understand anything, but you have got that huge data, and he says that, oh, this is 5% deficient, that is 10% deficient, all sorts of table is there. And you are finally the signing authority that everything is acceptable. So I think that is again a very dangerous area, because some cables might not be acceptable. You need to ask that if there is some 20% deficiency in one of the cable, for example, the elongation is less or force is less, whatever it is. In that case, someone should decide whether that is acceptable or not. So you have to either you do your calculations or get calculations from him that this deficiency is not going to matter for the entire thing. With this less force, okay, my rest of the design has got these revised stresses, or the top stress, the bottom stress, and so on. If that kind of situation is there, then I think it is acceptable. Another thing is, they ask you that, sir, when shall we do the stressing? Now, how can you decide? Because he has got some requirement and he has got some urgency. So he says that I want to do my stressing as fast as possible. But there is a requirement that at least 70, 80%, 75% concrete strength must be attained. And till then, some people keep on asking you, sir, shall we keep the centering till then or not? So you are not sure whether that beam can it take the self weight, or can it take the live load, or can the centering be removed. So all those issues are involved, and the result of that is you have to give decision, but you are not able to scientifically decide whether it is yes or no, whether the centering is to be removed or not, whether can the beam take its own weight or not. So all those decisions have got to be basically taken by a designer who understands pre-stress concrete as well as RC concrete. So I think it is a necessity that you properly put your mind into it and finally properly decide. In stage pre-stressing, particularly when you consider transfer girder, now it is going to take load from 30, 40 floors all above. So you have got firstly only the self weight, that is only the girder itself, it is cast, and now the contractor is after you, sir, I want to remove the centering. So you have got an issue, you say that, oh, pre-stressing is not done, what can I do? So there is an RCC beam, now it is not pre-stress at all. So someone must decide whether can the RCC beam take its own weight. It is designed for weight coming or load coming from 10, 20, 30 floors. So basically anyone who can rationally decide that yes, it is designed for much larger load, at least self-weight it can definitely take. So such decision PT designer will definitely not take. He says that sir, you decide. But that centering and shuttering is not my problem. So he only comes there with the cables, the jacks, and this I think that pump for putting the concrete slurry and so on. So all that he has got the equipment, but other things he says that is your lookout. So you must properly understand whether the stage pre-stressing is done at proper interval, whether the centering can be removed, and so on and so forth. So I think for all that purpose, there is a necessity that RC designer properly understands pre-stress concrete. Okay, I think that is one part of my presentation. I think if I have got time, then I want, okay, you want to ask something? Okay.
Hello. Good afternoon, sir.
Good afternoon.
Why in this PT system, in what cases vibration can be a problem?
See, for PT slab, there is hardly any difference in vibration of RC slab or pre-stress concrete slab. The stress level is so low, overall stress level, that you can consider vibration of PT slab same as vibration of any RC slab. The problem with PT slab is you are going to reduce thickness. The result of that is there is a more chance of vibration due to human walking or human usage and so on. So there are load cases available wherein you can consider under walking condition, will it vibrate excessively. So that load case you can consider. You can ask the PT designer also to consider that as one additional load case for walking vibration. And if that is okay, then you can consider it as.
Okay, thank you.
Yes. Yeah.
What happens when structure is subjected to lateral loads? Because if it is a slab, we can understand, but in case of girder beams or some beams which are of large span, so it cannot be designed only for gravity load.
Yeah, there are other loads also. So like your beam, if you have got beam under PT,
Yes, sir.
even floor beams or transfer girder, that is under PT. So they are designing it only for gravity load. But at the junctions or at other places also, forces are developed in your ETAP model. You will see that there are shear forces, bending moments and so on under lateral load. So you have to take those loads into account, the moment due to that, and provide for that. So your normal design for all the lateral load will hold always there. It will always have to be satisfied. But his contribution is only due to pre-stress, and that his basic criteria is only for live load, because ADAPT cannot handle three-dimensional frame. That is his problem. So he takes only the floor model and only considers that.
Yeah, rather we can do it the other way. So we can give him the worst condition forces and ask him to design for that. Indicate specifying the percentage of load to be carried.
You can do that. For example, total moment, you can give design moment. See, design moment is applied at the, at the support as well as at the mid-span and so on. So he is mainly worried about the mid-span moment. Normally at the ends, he generally considers it as a simply supported, or at the most some column negative moment is there. So if you give him moments under all loading cases, yes, that can be considered. But if the lateral load moments are very heavy, for example, and initially he will do pre-stressing to account for those moments which are not there. So there will be serious issue. That is why they only do for gravity loads. Because the pre-stress is an active force. It is unlike your reinforcement. Reinforcement is a passive resistance. So if the load comes, then it is in tension. If there is no load, it is unstressed. But unlike pre-stress, pre-stress is an active force. So you are generating a negative moment. And if the positive moment is not coming, then you have got serious issue. That is why it is not industrial practice that you don't give moment to him, because then there may be serious issue under intermediate states. Yes, please.
Uh, you told about walking vibration analysis.
Ah,
So,
yeah.
what can be the limit of that acceptable limit for the
I think
vibration?
that code has given the acceleration, maximum acceleration they have given in terms of micron per second square. So that you can directly get. ADAP software gives you that walking vibration as a standard load case. So as soon as you see the acceleration produced, then you can satisfy. I mean, you can be sure that it is within limit,
Okay.
because that is a serious issue for long span slabs where thicknesses are reduced from moment consideration, but the vibration is an issue for very long span. Many times that is an issue.
In the case of gravity, is there is any specification? Because we are dealing with one of the pathway or something in that we are struggling in that.
See, normally human walking is not considered as a dynamic load. It is normal load, okay. Like any other passage in home, also people keep on walking, or in gym also you will see that there is some dynamic activity. But that is generally taken at the vibration level itself. In the sense, you only consider the allowable vibration for human occupancy, and then see whether you are getting amplitude within that.
Sir, I have two questions.
Yeah.
First one is there is much debate on unbonded post tensioning and bonded post tensioning.
Yeah.
So, can you please throw light on the which one is better or which to be used in what conditions? And second thing, sir, post tensioning is its effect and its performance in seismic activity is not much recorded or studied. So how can we take contribution of PT tendons or PT in beams or in seismic design?
I think as far as the first question is concerned, see, you have got pre-tension, post-tension, and now you have got the unbonded. The pre-tension and post-tension are both bonded, while this one is now unbonded. So this unbonded has come into play only recently. It is the latest technology. Last, I think, 5-10 years, people are using it, and there is nothing wrong with the technology as such, because it has got one advantage, that your frictional losses are greatly reduced. So you are not able to, I mean, you are able to sometimes save on the pre-stressing cables to be used. Okay. So there is technology wise there is no issue on that. As regards the earthquake performance, or lateral load, or you can say performance of pre-stressed concrete girders, frames, and so on for earthquake, and there is enough document available that under earthquake conditions, the main problem with pre-stressed concrete is that it is not as ductile as a torch steel or mild steel, but even then it has got an ultimate elongation of about 7%. So there is enough margin available on that count, and in most of the cases, though you are allowed to take up to 80 or 85% of the ultimate stress as your stressing level, but normally people don't go beyond 70-75%, and then there are obvious losses of about 15-20% due to various causes. The result of that is there is enough margin for earthquake. So in my opinion, there is no issue for earthquake. You can straight away use it for zone 5 or in the old code. There is no issue. Okay. I think I will go ahead with my last presentation, and which is not a conventional type presentation, which is you can say a slightly different presentation, in the sense, I have been in the field for almost you can say 50-55 years. Out of that, 30-35 years I have spent in academics, and till then, of course, I was involved in industries. So in all my experiences in academics as well as industries and the interactions and so on, and last 15 years or so I am in industry purely, I have seen that people have various types of notions about technologies or about many things happening around it, And I have seen that many times, even highly intelligent people, highly experienced people, they have got some funny notations in their mind, funny ideas in their mind, even in technical matters, and they keep on carrying those ideas and propagate the ideas in a wrong way. The result of that is even those ideas don't die, they continue from generation to generation. So I have seen many such examples where otherwise a very intelligent person, but somehow in some areas he has got a gray, I mean he is not very clear about that, but still he forms some opinion about that. And then with his own logic, he finally tries to arrive at a conclusion, and then finally many times there are funny situations in that. So I have compiled such instances where people have come out with their funny ideas, but unknowingly that they were saying those ideas, and later on when they were told, oh, this is not the way it behaves, but it is acting, and so on. So there are many times misconceptions in our mind, or there are many times proper concepts in our mind, and sometimes there are horrible misconceptions in our mind. So I have got a compilation of such simple examples, and they are all, please remember, they are all true examples. There is no imagination involved. There is all the instances which I am quoting, they are properly recorded, or there are instances to believe that they are the true one. So I have got I think this is one simple story which you have been all hearing as a thirsty crow. I think the first story a child hears is about a thirsty crow. So we all understand that the crow was continuously dropping the stones in the big pot, and then the water level rose eventually, and then he had a proper water to drink. But we heard this story from a very aged nanny, you can say, a grandmother. She was narrating this story, and she was saying that the crow was so intelligent that as soon as he dropped the stone in the water will fly off, and the crow would catch that water. So she was carrying the impression that crow is so smart that he doesn't have to drop hundreds of stones to make the water rise level. But she was saying that all along, you drop a stone, some one or two drops may fly off, and the crow will catch that. So she was carrying that impression all her life, and then finally she realized at a very later stage that that's not the true story. We all know the story of the great scientist Newton, who thought that there should be a big opening for a big cat and a small opening for a small cat. And with his huge logical progress, he could not understand this simple thing that, oh, you can provide only one opening and the whole thing would be taken care of. But he was involved in his own work that he finally produces something which is so illogical. Even when Columbus traveled from Europe to America, and he had in mind a goal that he wanted to reach India, the Far East, but he has started on the west side because he believed, I mean, he knew that earth is round. So he thought that, okay, if I want to go to east, I can start from west and eventually come to the east side. Hello? Hello? So eventually he would reach east. So he carried his crew in the ship, but they were not ready to believe that earth is round. They were saying that if earth is round, if you go on the other side, oh, your head will be hanging down and you will fall down. They were all believing like that. So he had a hell of a time to convince them, oh, don't worry, even if earth is round, you will not fall off if you go on the other side. Because they were thinking that my head is on the upper side, but if you go 180 degrees on the other side, oh, my head will be simply hanging down and I will fall down. So they were all afraid that they will fall down. But he had to finally use all his means to take them to of course he could not reach the Far East, he reached only America, and there the journey ended. There is another story of Aristotle, where Aristotle has written 2000 years back, and that is a part of the medical education reference, that he has written there that women have less number of teeth than men. He has written that 2000 years back, and 2000 years people were following, yes, yes, whatever Aristotle says is true. And eventually, when in 18th century or 17th century, someone had the courage to count the number of teeth maybe in his girlfriend's mouth or his wife's mouth. So they finally realized, oh, this is not correct. For 2000 years, people were carrying the impression. Even Aristotle could have done the same. He could have just asked his wife, open your mouth, and the wrong information would not have disseminated all these 2000 years. But he has written very clearly that women have less number of teeth, and in those days the equality was not there, so people thought that yes, yes, it is a possibility, God might have done that on some purpose and things like that. In 1930s, when there was a big earthquake in Bihar, so we all know as a student of civil engineering and structural engineering that earthquake has got some physical reasons, that there is the plate movement and then the energy release and so on. But this politician of great stature has indicated that, oh, these Bihar people, they don't believe in God, they don't believe in religion, and that is why there was an earthquake. So he carried that impression that if you are not a person believing in God, then you will get such kind of calamities like the earthquake and so on. I had an occasion to work with one of my junior colleagues. So we were designing some water tanks for a company. So various types of, various sizes of water tanks were there. So I thought that it's a great opportunity for me to compile the data. There were more than 100 tanks with capacities ranging from 25 cubic meter to 5000 cubic meter. So I said that great opportunity is there for me to collect the data and indicate it in terms of cement consumption, steel consumption, and so on and so forth. So I gave this assignment to one of my junior staff member. In the sense, he was at least 10-15 years in the field, in the academics, and he spent all his time, 4 or 5 days he took to take the drawing and work out the steel consumption. And finally he told me, sir, the steel consumption is 8032 kg per cubic meter. So I said, 8032, you know what is the density of steel? Then he said, yes, it is 7850. I said that 7850 is the density of steel, and you have got steel consumption as 8000 kg per cubic meter of steel. Don't you think there is something seriously wrong? He just said, no, sir, this is the drawing. I cannot say that. So he could not understand that even 1 cubic meter of steel itself weighs less. While in 1 cubic meter of concrete, how can you have steel which is weighing more than that? So that is a terrible mistake. We were proof checking a design of one of the very renowned company in VZTI, and they were designing some rock anchors. So they have brought to us a rock anchor design, and the company is well established into that. The in charge of the design was a very senior person, elder than me in those days, and they had produced a design. So they were saying that it's a 25 diameter Tor steel, which will be drilled. The force to be carried is 40 ton. So I said that 40 ton force, let me see your calculation. So what he has done is, he has drilled, he said that we will drill a hole which is 40 meter long. In 40 meter long, it will be all filled with concrete, lean concrete, and the bar will be there. And bar has got enough anchorage length, 40 meter anchorage length. The bar is only 25 meter diameter. So he didn't understand that there is other mode of failure. The bar itself will break, maybe at 15-20 ton, the maximum ultimate load it can take. But he was only relying on one type of failure and produced a design which was about to be executed. And then they all realized that, oh, this is absurd. I mean, you can't drill infinitely and then say that the bar can take 100 ton load. That is impossible. We were involved in designing of a dome. So it was a steel dome, and an architect has planned that dome almost 50-60 meter diameter. So we had planned that, and there was a ring at the top, as you know all, that there will be arches, they will be meeting at the top and so on. And it was a stable structure. The architect had a very queer queries. He said that I understand that the ring is supporting the arches and the arches are supporting the ring, but who is supporting both? So he was asking. So I said that, come on, you and me will support the arches, don't worry. Because he was not able to understand that they are mutually supporting, but he was very senior architect. But he was having that impression that I understand. Arches are supporting the ring is supporting the arches. But who is supporting both? So he had that impression all along. I was involved in the investigation of a small accident which has occurred in one of the companies. So they had an assignment of lifting few tons of load, maybe 1500 kg or so load. So they had thought of an idea that, okay, in the end we will have a simple vertical columns, and instead of having a beam and so on, we will take a string or we will take a cable. So we will have a cable, and from the cable we will lift the weight. So they tried to make the entire arrangement. So the columns were erected, the cable was suspended from that, and then with a jack, with a pulley and check device, they started lifting the weight, and the whole thing came down. So they brought me, sir, called me and said that, sir, there is an accident and you just indicate what is wrong, because the weight is only 1500 kg. We have got columns which can take to 5 ton, 10 ton. So there is nothing wrong with the column. Still, how the column failed? So when I saw that, I said that your cable is exerting all horizontal force. He said, but we are applying vertical load. What is wrong with that? So he was not able to understand what happens with a simple dombari, as we call him. That you have seen that dombari, that small girl which walks on the rope. So when they establish the end supports, so they have got a cable going to ground on the end. The result of that is the cable extends large horizontal force on the supporting system. To counter for that, they have got the tie down. But this highly qualified engineer was not able to understand that you need this tie back. The dombari knew it through his experiences and so on. One of my colleague had this problem that he taught strength of materials for many years, and you know this simple moment area theorem. So we have got this moment area theorem, and moment area theorem is a very simple theorem that a moment of M over EI diagram about one point gives you deflection of that point with reference to tangent at some other point. So he was trying to apply it to a fixed beam. So this is a fixed beam, as you see, and you have got a UDL, so there is a bending moment diagram due to that. You have got the end moments, okay, fine, so far so good. So he said that if I want to get deflection of the midpoint, that is center, with respect to the tangent at the support, so what I will do, I will take this parabolic area. Its centroid is at 5 by 8 from this point and 3 by 8 from this side. Okay, fine. So he said that I will take moment about this point. That will give me deflection of this point with reference to tangent at that point. Fine. He said that this deflection is same as this. As a physics I know it. Both the values are same. Here this point is above this tangent and this point is below that tangent. That's all is the difference. It is a deflection with reference to tangent. It can be above or below. But he then reasoned out it without going into the detailed calculation. He said that if I take the moment of the rectangular is the support moments, which is a rectangle, whether I take moment about this point or about that point, the moment is same. It's a rectangle. But for parabolic part, he said that if I take moment about this point, it is 5 by 8. If I take moment about that point, it is 3 by 8. So moments of this area will not be same about both points, but moment of rectangle are same about both points. So he concluded, that means moment area theorem is not applicable to fixed beam. Of course, that is obviously, as you know, it's not correct. In one case, the moment of this area is larger than the rectangle area. In other case, it is the smaller of the, but the difference is same. So difference is same. Only in one case it is above the tangent, in other case it is below the tangent. But instead of spending some effort for almost 25 years, he was arguing that moment area theorem is not applicable to fixed beam. Very queer situation. Then there is, I think this is very simple. Okay. Then many times there are situations where for a long time people carry some wrong notion. You know perhaps a story of George Bernard Shaw where there were two ladies friends. One was very rich, other was very poor. That poor lady borrowed a necklace from her rich friend and wanted to go to a party. So she went to the party and something happened and she lost the necklace. And she was so afraid, that poor lady, that, oh, what to do? It was such a beautiful necklace. So I have lost it and now I am lost. So she somehow went here and there, finally went to a jeweler and brought a new necklace. She spent fortune on that, took some loan and returned that necklace after a few days to the rich friend. And then time went on and on and on. And this poor lady spent her entire lifetime earning, doing extra work and repaying the loan. After 20, 30 years, they again met each other and the rich friend said that, oh, you are looking so tired, so old, or what had happened? We have not met for so long. Then she said, it is because of you. Then she said, how I am responsible? Then she said that, you remember I borrowed that one necklace and then I lost it. Then that rich lady said, oh, that was a fake, that was duplicate. Why you did not ask me? Oh, then she said that I thought that it is like that and the whole lifespan is spent on that. Likewise, people spent all their lifetime in carrying such notions over here. So I had an occasion to attend lecture of a very senior professor who was, I had a lot of respect for him. So he was teaching simple problem of the trusses and it's a real story. So he was indicating that these truss, all the members carry only axial force, wonderful. So axial force means the member simply elongates or contracts, nothing more than that. So he carried impression that if you take a truss, apply some load on it, okay, the member only extends or contracts. Okay, simple logic, everyone knows that it's only axial force. So he said that even after the deformation, it is a great wonder that every member remains parallel to itself even after deformation. So how it remains is I am not able to explain. He carried that impression that the member may go down this and that, but it will remain parallel to its original orientation. He carried that impression. He was a professor, produced almost 25 PhDs, and very brilliant and otherwise very knowledgeable, but carried the impression that the truss members remain parallel to its original configuration, original orientation, even after applying load, because he thought that the member only elongates or contracts. So he was not able to accept that it can bend, but still it will be subjected to only axial forces. But he carried that impression, and after a lot of arguing, then finally he realized that, okay, yes, perhaps I have carried it wrongly all along. I think there are only one or two items now, very funny. In one of the consulting engineering company, there was a big argument going on and I happened to be there for some work. So they were all arguing that there is a pre-stressed concrete slab. So there was force applied on both sides. So the junior engineer was asking, sir, there is a jack on this side and there is jack on that side. So you are applying a force P and there is a force P. Okay, both the jacks are applying. So is it a 2P force or a 1P force? And there was heated discussion. So, there is no need for a decision. We all know that it's only force P. But there was a discussion, serious discussion. And then finally the boss said that, I think you take for me one side. that if you stress from one side only, okay, you take P. But if you apply jacks on both sides, oh, that is 2P. That is, he said. And then finally they settled that, okay. He said, at least you be on the safer side. You are calculating stress on the higher side, so that's fine. That is, I think it's okay. You are not making mistake to cause any harm. So he carried that impression that the force is 2P rather than P. I had an occasion to design a foundation for a 200-ton compression testing machine. So it is a simple foundation. As you know, many times they keep it on the floor itself, but the company had a requirement, oh, you design the foundation. So I designed the foundation. He said, you also get it proof check from somebody. So I went to a renowned institute. I knew the people there. So I said that it's a simple foundation. So, but the person who I said, yes, I agree, but you have to get a signature of the big boss, the head of the department. So we went to him. The big boss asked, oh, what is the load? He said, 200 ton capacity of the machine. What is the bearing capacity of soil? So he said, it's 20 ton per meter square. Oh, 200 ton, 20 ton. So you need a foundation which is 10 square meter. Okay, he carried the number. Then we were just perplexed, sir, what are you saying? He said, no, it's very clear. It is 200 ton load you are applying. It's a reaction frame, so there is no need for, there is no load transfer on it. Then the professor whom I had approached, he told me, you just go out. I think he is not in his proper mind. I will just convince him, don't worry, but it will be signed, you go away. So I coolly went away. And then next day there was a signature there. And so I think that's all right. I think many of you must also be having such instances in your life. So my earnest request to you all is that no matter what impression you carry, you discuss with somebody at least in your lifetime, so that you don't carry such impressions all along and then perpetuate those wrong impressions. I think thank you very much. That's all.
Before starting Professor Singh's next lectures, I would like to do my customary duty of vote of thanks before that lecture, so that the next session can be endless. So we don't have any pressure of ending the session. Yeah. So, and before that, I would like to give some information for the vote of thanks. See, this seminar we have done after COVID area, the first workshop which is done in physical form. I'm glad to inform that we have received 41 registration from out of Bombay. So, these are 41 of yours of the total 200 capacity is from out of Bombay. They are spent their own money, come here, stayed here, apart from our charges.
Hello.
So,
this can be called as a magic of name, Dr. Yogendra.
Yeah. So for that is obviously that credit is to Yogendra Singh sir. But I'll just like to read that from where the people are within 2 minutes. There are 4 people from Ahmedabad, 1 from Aurangabad, 8 from Bangalore, 1 from Bharuch, 2 from Bhopal, 1 from Chennai, 2 from Delhi, 1 Ernakulam, 3 Guntur, 1 from Kolkata, 1 from Kozhikode, 1 from Madurai, 1 from Nagpur, 1 from Nanded, 2 from Nasik, 6 from Pune, 1 from Patna, 1 from Rajkot, 1 from Surat, and 2 are from Kerala. So these just wanted to inform you that this is so it is truly a so we can call it as a, we are very happy to announce that. Then this we are definitely basically very thankful to our sponsors, Midas Research and Development Center, Hilti India Private Limited, Tanaji Creative Turnkey Projects Private Limited, Gubbi Civil Engineering, and BDA, who have helped us in arranging that by contributing some money. Obviously, this VJTI we can't forget, because VJTI is our co-host also. So, Vijay, thanks to Dr. Professor Sangle sir, who had allowed us to use this auditorium and other services and this beautiful renovated auditorium, I can say. We are thankful to our caterers and other service providers, and lastly, but not least, our own volunteers who have done, as usual, a lot of work. Thank you. I'll request Dr. Yogendra Singh now to take charge of this hall till whatever times is possible.
One more announcement is whosoever will ask last question, he will have to put off the light and close the book.
Thank you, Parulekar Sab. We have two options. Some of the points are remaining still in modeling and analysis, especially related to 16700. And then I also have base isolation design. So that is also a new code. So that is more or less like a change, because it is changed from nothing. Earlier there was nothing, now we have the code. So there is a change. So both the things I wanted to cover, but there are some important points left in modeling and analysis. So I will go back to that. And let's take up so one of the systems which is covered in IS 16700 is frame tube system. So frame tube systems, I don't think, you people will correct me, if we have used in any building so far in our country. We have not used, I think. But it is, rather it was a very popular system in 60s, especially when these skyscrapers were coming in US. So this system, it consists of closely spaced columns and beams along the perimeter. So the idea was that that the moment of inertia against lateral load we have to increase. So whatever columns are in the interior of the building, we put those along the perimeters. So we have all the lateral load resisting columns and the beams along the perimeter. These are large size beams, sizes more than a meter, and beams are also quite deep. So it is like sort of coupling shear walls all along the perimeter. So it can be visualized in two ways, that a beam column frame, 4 beam column frames are arranged on the 4 sides in the form of a tube, or it can be visualized that it is a hollow concrete tube with punctures for windows, openings for windows. Both ways it can be done. So this system has some peculiar characteristics. It has very good stiffness and strength because it consists of closely spaced columns and which are interconnected by deep spandrels, so behaving like coupled shear walls, and it is arranged along the perimeter. So its effective moment of inertia increases. But it has lack of shearing rigidity. It is hollow sections, we know. Hollow sections have the problem of shear lag. So same phenomena of shear lag is observed here also. So suppose this is the direction of the loading, earthquake or wind load can come in both the directions. So if it is subjected to an earthquake load in this direction, then this frame will act as BAV and this frame will act as flange. So if the direction of the loading is orthogonal, perpendicular to it, then the role of BAV and flange will change. And ideally, when it is subjected to this type of loading, the distribution of the axial forces in the column should be like this. In the flange, it should be uniform, and in the BAV, it should vary linearly. That should be the ideal system. But real force does not behave like this. The variation is something like this. So the corner columns are having higher axial force. The columns which are in the middle of the flange, those are carrying less force, and those corners which are, the columns which are in the flange, in the web, those will having variation of axial forces like this. It is simulating the warping of the cross section due to shear deformations. Because it is not having infinite shearing rigidity, the spandrels which are connecting the columns, they can't make all the columns to deform by the same amount. There will be some leaking of that deformation as we move from corner towards center. So this phenomena is known as shear lag. And very interestingly, it was observed that this phenomena is there up to lower 1/3. And in the top 1/3, it is opposite of that. The central columns are having larger force than the corner columns, and this phenomena was already reported, and it was known as negative shear lag. And my PhD was on that. I explained for the first time that why negative shear lag occurs, and that was my first paper, which was published in ASCE during PhD. So interesting phenomena was that there is a negative shear lag in the upper portion, and this positive shear lag itself gives rise to negative shear lag, and this shear lag phenomena is there in all tube and flange type of systems. Even in steel girders, we are having this. In box girders, when we are using box girder for bridges, there also the phenomena of shear lag is there. So initially, when people were using earlier days, when this system was invented, and this system was proposed by an architect who was from Bangladesh, Professor Fazlur Rahman Khan. So Professor F.R. Khan gave this concept, and it became so popular that almost all the buildings during that time, those have used this system. And with this system can be followed in steel as well as RCC, and the calculations there were done by beam theory. So we were assuming ideal beam behavior, and then deviation from the ideal beam behavior through this charts were prepared for this shear lag. Nowadays that is not needed because we can make a computer model of that, and this phenomena of positive or negative shear lag will be automatically considered. Only thing is that we have to keep in mind that I want to highlight here that the distribution of axial forces in the columns is somewhat peculiar in this case. So if that type of variation you are getting, it should not be a surprise for you. That type of variation we get. In the bottom portion, the central columns are taking less load. In the top portion, the central column starts taking more load. And it may so happen that in the top portion, the corner columns undergo negative tensile forces on the compression side and compressive forces on the tensile force. So that phenomena happens, which is quite surprising. But it is simple elastic analysis. The advantage of these systems is in terms of stiffness and strength. What is not known is how those are going to behave after yielding. So that behavior I have not seen. I have also not worked on these systems after that. I started working on other structural systems. I have not seen others also to work on the system where they can see that what type of ductility we are expecting here. So how good this system is very efficient for wind, and for taller structures where wind is governing, there is no doubt. But how good it will be for earthquake, that is yet to be seen. Although our code asks for this system in case of high seismic zone, when we are going beyond a particular height, it makes this compulsory. But what should be the response reduction factor? Can we use 6 for this also? It's not clear. Although, and our IS 1893 is also not providing any separate response reduction for that. And one of the famous buildings, which is no more, those twin towers, World Trade Center, that was the tallest building, and that was made in steel using frame tube concept. Yes. No, beams are deeper, but that doesn't mean that those are stronger than the columns. Okay, so, but no such study I have seen where they have set rules that how it will be designed, how to ensure strong column weak beam, whether strong column weak beam is necessary or not. Of course it is necessary, we understand, but deeper beams and the columns are closely spaced, so it will act like a coupling beam, so it will fail in shear. So the detailing, normal beam column, normal detailing which we are using in our beam will not be applicable. We have to use, in most of the cases, we have to use the diagonal type of detailing if we are using RCC frame tube concept. So it will be detailed like a coupling beam. Then another concept is this tube in tube system. So where we have the outer tube of frame and inner tube of shear wall. So in a tall building, the service core will be very large. So that service core we can enclose by shear walls. We cannot provide shear walls on the perimeter. So this is again a very useful system where we can achieve good torsional rigidity also by providing this tube on the outer periphery. And negative shear lag is the limitation of this system because because of lag, we are not able to utilize the columns fully, the central columns fully. So to take care of that, the concept of truss tube and multi-cell tube is proposed. And it is believed that the future building which we are thinking of to going up to a kilometer, so that building will be a combination of truss and tube. Both the concept if used together, this will we can achieve maximum height. So to reduce the shear lag effect, another way is providing multiple webs, because where the webs are connecting with the flange, at those locations we get the maximum column force. So we have multiple webs, or what we call multi-cell tube. And this is another one of the tallest building, sometime it was the tallest building, and this is having multi-cell tube. And the architectural geometry is created by dropping different tubes at different heights. At the base, all the tubes are bundled together, so it is called multi-cell tube or bundled tube. Then there is a comparison of the optimal heights where different types of structural systems will be economical. So it is not restrictive like it is there in our code that this in height range we should use this. But the efficiency, in what order the efficiency will go on increasing in steel systems, so that is given in some of the books. In case of low-rise buildings, we can go for normal frames, maybe pin jointed or rigid jointed frames. Then we have this eccentrically braced frames. If we want to go further higher, then we can have eccentrically braced frame with outriggers. Then we have this tube system. So in tube system, we can have a full complete tube, or we can have these outer columns arranged in the form, in the shape of C. So two channel like shapes, or we can have a closed frame tube like this. Then further high, we can go using multi-cell tube. And when we go for this trussed tube, so in addition to this tube, we are having a vertical truss also. We can go further higher. So efficiency wise, this is the hierarchy, this is the order in which the efficiency of these structural systems is increasing. So in steel, we have eccentrically braced frames. In RCC, the eccentrically braced frame is replaced by shear walls. So that's the only difference. Otherwise, hierarchy is here also, and we do not have pin jointed frames in case of RCC. So RCC, we have frame, then we have shear wall, then we have frame and shear wall, then we have framed tube, then tube in tube, and then multi-cell tube. So this is the order of increasing efficiency. Theoretically, you can use any system up to any height, and it has been proven also, as I said earlier also, that Type A 101, they have used frame system to achieve more than 100 stories. So that can be done, that is possible. But it is considered that optimal ranges are like this. So if you want to go for a tall building, if you want to construct a 100-story building, in some form or other, you should try to use tube concept. And our 16700 is also, although problem with 16700 is that it is restrictive. It has said that in this zone you cannot use anything else other than this structural system. So that is perhaps not good for the profession, that we are so restrictive that we are not allowing, because many innovations are possible, different structural systems, and that's where the architect and the structural engineers have to show their talent and their out-of-box thinking, that what structural systems, even new structural systems can be discovered. The principle is this, that we have to enhance the moment of inertia, or we have to transfer more and more load through axial action. So this is currently the limit given by our code. It is also in the similar order which I have shown, but here a restriction is there that in this height category and this zone, this type of structural system will be used. Then other issue which is not yet there in our code, that is role of floor in lateral loads. Role of floor under vertical load is very well established, and Professor Gadgil talked about PT slab. So PT slab is coming out in big way in our industry, especially in southern part of the country. Perhaps in Delhi I have not seen it that common, but here in Bombay it is quite common. So that is okay, but what we have to understand is that slab also has a big role in lateral load, earthquake load as well as wind load, and that role is that it distributes the load in different lateral load resisting elements in proportion to their stiffness. If the slab is not there, then the load in different lateral load resisting elements, different frames and shear walls will be distributed in proportion to their tributary mass. Whatever mass is attached to a particular member, only that inertia force will flow to this. But what slab does, it distributes the forces, lateral forces, in proportion to the stiffness of different members. So the force during earthquake, I mean, one question which we are also discussing in class with our students, that where does the earthquake force act during earthquake? So commonly the answer is at the CG, but earthquake doesn't know the calculation of CG. So earthquake is acting, it is an inertia force. It is acting at each mass particle. So earthquake force does not act directly at CG. If the building is having only translation, then the acceleration at a floor level is constant, it is same. So if there is no torsion, then the resultant of the inertia force will be same as the resultant of mass, or it will act at the CG or center of mass of that floor. But if the building is having a torsion, then the acceleration is no more constant on the floor. The flexible side is moving more, the rigid side is moving less. So acceleration on the flexible side is more, and the point of application of load of earthquake load will shift towards flexible side where accelerations are higher, and that's what we call dynamic amplification of torsion. And in the torsional clause there is a factor of 1.5, and in the revised code that is being increased to 1.8. So that is because of this difference in the acceleration which is occurring. So earthquake force does not act at the CG or center of mass. It acts at each mass particle, and it is proportional to mass and acceleration. So if acceleration is constant, it is proportional to mass, and then its resultant will coincide with the resultant of the mass. Otherwise its resultant is not going to coincide with the center of mass. So it is acting at each mass particle, but it is being registered by different lateral load resisting elements, for example shear walls, at their location. So who takes this load from the point of application to the point of resistance? It is the slab which does that. So that role of the slab we have to keep in mind. Our code is not very clear about that, so we have to keep that in mind, that the floor needs to be designed for this in-plane force also. The slab needs to be designed. When we are doing PT slabs, then if the whole plate is being pre-stressed together, then it is okay. But if we are pre-stressing in the pieces, then at the boundaries we have to understand that it will not be able to transfer the forces, and we have to do proper detailing there. So two situations or two locations in the floor are important. The one location is when the floor is getting connected to a shear wall, because shear wall is registering lot of load and the floor has to collect the load from different points wherever it is acting the inertia force and transfer it to the shear wall. So that transfer takes place at the interface of the shear wall and the floor, and that interface needs to be checked. So when we are checking the stresses in floor, we have to check not only the normal stresses, compressive and tensile stresses, S11, we have to also check the shear stresses, S12. That is very important, because many times the failure occurs between the floor and the shear wall at the interface in the shear. And sometimes if that interface is not enough, or we have, many times we have a cutout adjacent to a shear wall, then the connection between shear wall and the floor is not adequate to transfer that load. In that case, we have to use collector elements. So collector elements, those extend both directions from the shear wall into the slab, and those transfer the load from the shear wall. Those collect the load from the floor, which has taken load in turn from the different mass points. Those are transferred to the collector elements, and collector element is transferring that load to the shear wall. Now, in plane rigidity of the slab, this is an extreme example where the building, a hypothetical building is considered, the slab is very long and it is subjected to inertia force like shown here. So then the slab will act like a continuous beam. The beam which is supported on these frames and shear wall at the end, and it is subjected to this much load. So the deflection will be like this, and this deflection will decide whether we can treat it as rigid or we have to treat it as flexible. That check is there in our code. But this will also subject this beam, this floor to be moments about vertical axis. So in plane moments. And those in plane moments will be registered by the longitudinal reinforcement running along its length on both the sides. So a continuous reinforcement along the chord. So this length will be called chord. So along this, a chord element is to be running. So that's why when we are talking about flat slab buildings, our code is very clear about perimeter beam. So that perimeter beam has to act as the chord element. So the reinforcement provided in that chord element will be continuous. And the detailing which we are following in our slab, when we are providing the reinforcement, we are generally providing reinforcement in panels. So each panel is independent. So one panel, that reinforcement we cut at the center of the beam, and then another panel reinforcement starts. That also needs to be checked, that whether at that location that reinforcement is adequate to take this much force or not, especially when this chord beam is missing. So in case of frame buildings, usually we will have a beam running along the perimeter. But if somewhere that beam is discontinuous, for example, there is a corridor in between and we discontinue the beam there. So at the perimeter we should continue. We should not discontinue the beam along the perimeter of the building. So make sure that one beam is running all around the perimeter, because that will act as tension reinforcement when our slab is trying to bend in its plane, or it is bending about vertical axis. So like this. So this reinforcement on these two sides, this will act as tension reinforcement or chord reinforcement when the slab is subjected to in-plane bending.
Also you have to column STP peri beams you have provided, or edge you have to?
That cantilevered portion can hang out, but
beam should be there.
Beam should be there. At the support of that cantilever portion, the beam should be there. Thickening of the slab, I mean, that needs to be checked. So you can calculate how much, so you can calculate the bending moment, you get the bending moment, then you know the depth. In this case, the dimension of the slab will act as the depth. You can calculate how much reinforcement is required, and that much reinforcement should be available, either in the beam or within the slab itself. Sorry? Column drop, you mean column strip? Column strip. So if you are having perimeter column and there is no perimeter beam, although perimeter beam is required by our code. We will not have any building without perimeter beam as per our code. But suppose, hypothetically, we are discussing that in a building if perimeter beam is not there, then the reinforcement in that column strip should be sufficient to take care of this bending about vertical axis, bending of the floor about vertical axis.
We will connect with whatever the column drop thickness is there, same drop thickness we will connect throughout the peripheral with forward extra reinforcement, panel beams.
But it should be checked.
Yeah.
What I am saying that calculation need to be done for this action of the slab also. Most of the cases it will be okay, but in some cases it may fail. Then if we have the shear walls here, we also talked about the shear transfer. So the force will be transferred from slab to the shear wall through shear action here. And that shear action will not occur only here, it will continue along the length of the slab, along or in the direction of the shear wall here. So there will be a strip of the slab which will act as collector elements. And the dimension of that strip can be obtained like this. From the center, if we draw a line at 45 degree, so where it is intersecting this line, the reinforcement which is within this strip, this reinforcement should be able to take. Okay. Oh, sorry, I have missed. I will take the pointer. Okay, I think now you can see. So if we draw this line at 45 degree, where it is intersecting the dimension of the shear wall, this will give us the effective width. The reinforcement within this width will be responsible for transfer of the shear force into the shear wall. And part of this force will be transferred as shear, part of this force will be transferred as tension in this reinforcement, and part of it will be transferred as compression on this side. So this compression, tension as well as shear together, that should be adequate to transfer that load to the shear wall. In same effect is there in the backstay. We have discussed a lot about backstay. Only thing I have to add there is that in addition to S11, please also check for S12. The shear stress also needs to be checked. Shear stress should also not be excessive. So shear stress S12 should not be more than tau max at any point, because if it is tau max, it will fail in shear. And then it should be checked for the shear reinforcement provided as per the slide, the previous slide which we discussed. I will skip this. This also we have discussed, openings. Yeah. Other thing I want to talk about is how to design podium and backstay, particularly from the point of view of BB bar by BB correction. So the code says that we have to match the base shear, and in case of buildings with basements, the height of the building is to be considered above ground level. So how to match that in case of buildings with basements? So in case of buildings with basement, two models are possible. In one model, I can model the basement and the tower together, or I can do a substructuring method where I model the tower separately and the basement separately. These all we have discussed, so I will skip. I will go straight to that model. So either I can model the basement and the tower together, that is also possible, or I can model the tower separately. So if I am modeling the tower separately, assuming it to be fixed at the top of the basement at the ground level, there is no issue in matching the base shear. I will get the base shear from the numerical model. I will calculate the BB bar using the period formula given in the code, that is valid. I can just scale it. up to that level, and then I can transfer the forces which I am obtaining at the base to the basement, and basement analysis I can perform separately. The issue here is that what inertia force I should apply on the basement. So one thing is that as we go down in the ground, the acceleration reduces. We discussed that code allows to reduce it up to half at 30 meter. In proportion, we can reduce the acceleration. Another is that what period I should consider for the basement. That's another issue. Because that reduction gives me the value of Z at a depth. But what value of SAYG I should take? So one thing we understand that the basement is very rigid as compared to tower. Not only because soil is there, we can, even if I ignore soil, even then because it is having lot of length of shear wall in form of retaining wall. So that retaining wall which I am providing on the perimeter of the basement, that will also act as shear wall. So very long shear wall I have, so it is quite rigid. So question is, if it is very rigid, which value of SAYG I should use? If the period is more than, or sorry, period is less than 1/33 second, frequency is more than 33 hertz, then I can take SAYG equal to 1, or rather SAYZ equal to 1, and the value of AH will become equal to Z at that level. But if it is, period is more than 1/33 seconds, then it can be anywhere between Z to 2.5 Z, in that range. And it makes a lot of difference. So if I consider 2.5 times Z, it is on conservative side. That is okay, because SAYZ value cannot be more than 2.5, whatever is the period. So if I take 2.5 Z, it should be okay. But in some cases, that becomes too much. And I was carrying this impression, Gadigal sir was talking about the wrong impressions you carry throughout your life. I was also carrying this impression that because the length of the this retaining walls is so much that it doesn't matter. Whether you take a 2.5 Z, even then it will cause negligible stresses within those shear walls because the length is so much. But when we are having this landscaping, a lot of soil weight we are also putting over the top of the basement. The forces may be so high that it is crossing the maximum reinforcement limit, even with such long basement retaining wall. So these forces are really very high if we consider 2.5 times Z. So what we did, we tried to compare the two models. The first model where we are comparing, we are modeling the basement and tower together, and another model when we are modeling basement and tower separately and then transferring the forces from tower to the basement. When we are modeling together, we have to be careful regarding the scaling of the base shear. So in that case, scaling of the base shear is to be done at this level, not at the base, because the period formula which is available in the code is for the tower portion, not for basement. So we will calculate BV bar at this level and we will scale the story shear. We will calculate the story shear here at this level, the first story of the tower immediately above the basement roof. That base shear we will match with BV bar. So scale factor will be calculated like this. So we did one simple exercise. G plus 19, 20-story building was taken. Sorry? Slide? Previous slide, okay. Any question here? So we considered SAYG 2.5 because that is on conservative side, and there is no way to obtain the period. If we model this separately, suppose I am modeling the basement separately, then also I am not able to calculate the period accurately because the period will depend not only on the basement, the period will also depend on the tower. And until unless I make a combined model, I will have no idea of the period which will be applicable for the basement. So conservatively we can take a value of SAYG equal to 2.5, and if you carry the same impression as I was carrying, you can be happy with this, that even if I am considering 2.5 times Z, it doesn't matter because the length of the shear wall is so large that hardly it will give any stress, and even the minimum reinforcement will take care of that. But I was surprised when the shear stress came out to be so large that the maximum limit was crossed.
Sir,
Yeah.
so we calculate the missing mass participation also in these cases. So we get the time period in the frequency range in that case for the substructure. So we analyze superstructure, substructure separately in two models. So is that way we have to follow or how?
Okay, I think once I finish this example, then that will be clear. So what we did, we make a combined model of, we did two analysis, one the tower and basement separately, and another the tower and basement together. And we studied the mode shapes here. So in the two analysis when we performed, in one case we consider 2.5 Z on the basement, then we are getting this much base shear, 3,500. When we did combined model and did considered all the modes to get almost 99% mass participation, so that we have sufficient mass participation, and did modal analysis and scaling of the base shear in the first story of the tower, that means above the ground level. Then the total base shear which we were getting at the base of the basement was 1876, roughly double the base shear. So base shear in the story shear in the tower portion is same in the two cases, that is not changing. But in the basement portion we are getting lot of difference because of this. And to understand this, we have to understand the different modes. So when we have the combined model, you can see here, okay, this is tower model. So when I have modeled tower only, I will come back to that later. In the combined model, if we see, there is participation in the initial mode, there is the mass participation here, we can see, then it is almost 0, and then in 42nd or 47th mode, we consider up to 300 modes. So in 42nd and 47th mode, we are getting participation. This participation is coming from the basement. So basement starts participating somewhere here, and the period here is 0.048. Now 0.048 is, second is such a period where neither it is less than 0.03, so that I can say that I can take equal to Z, nor it is 2.5 times. So that's the problem. So if this period was less than 0.03 second, then I can take a missing mass correction using Z value, multiplying it by Z value. So a static missing mass correction I can do. But in this case, that static missing mass correction is also not applicable, because it is more than that. It is somewhere in between. And if you look at our code, in our code it is 0.01 to 0.1 seconds. It is considering it constant at 0.01. So missing mass correction we can apply if this mode, the frequency which we have obtained up to 33 hertz at least. So those masses which are not being excited even up to 33 hertz, on those masses we can apply missing mass correction. These cannot be covered by missing mass correction because this period is coming somewhere in between. So we did the modal analysis, and in modal analysis whatever is the corresponding period and the modal mass, that will be taken care of, and what we are getting is 1875 and 3500, something like that. So almost double the shear is there. And we can understand if the mass of the basement is larger, we are having soil mass at the top of it for landscaping, then the period will also elongate and the shear force will be much more. So there this becomes even more important. We can get lot of advantage when we are doing modal analysis. So a combined model with modal analysis is recommended. That's the moral of the story. Then when we are multiplying, when we are having multiple stories, multiple towers, then it becomes even more complex. So backstay effect is fine. How to calculate the forces on the basement? So there the number of modes will be even more, because each tower will be vibrating separately, and then once all those tower modes are obtained, After that, we will get the participation from the basement modes. So basement modes will come even after that. But it is worth, we should go that, or alternatively, if we don't want to go into that, we are not able to excite the adequate number of modes, we should go for direct time history analysis. In that case, all the modes are inherently considered. Only thing is that the computational time required will be much more. So, which load? Yeah, that is mass. Yeah, that is mass source. Yes, why not? That is to be considered. So whatever filling load you are having at the top of your basement, that is to be considered in mass. Sorry? Yeah, it will be made. Actually, the true model, not true, a more realistic model would have been where I am modeling the soil also. So soil was also modeled either using spring or using continuum elements. I have to model soil, then I have to model the retaining wall, and then I have to model the tower. Okay. That will be even more complex. It will take even more computational effort and time. So we are not modeling soil here. There is general understanding that soil we will not be modeling. We will be modeling retaining walls, and whatever masses are there either at the top of the basement or within basement. So all those masses, all those mass sources we will consider. Yeah. So that's the next thing. If I model the soil, I can reduce it further. So if the stresses in the basement walls are really a problem, before that I have not thought about it because I was having the impression that it's not critical. But because it is critical, reinforcement is coming, and this is large shear wall, and if you are providing more than required reinforcement, you can have a lot of economy if you can do the proper analysis. So if we do a proper analysis, taking into account the soil resistance also, we can save a lot of reinforcement in the basement. So that would have been ideal model, where I am modeling soil also either using springs or continuum. And then this. But I can't say that because I have not modeled soil, so I will provide reinforcement less than what I am estimating. If I am making a simpler model, I am doing a simpler analysis, then I have to provide reinforcement as per that model. Even if it is conservative, I have to provide that. If I want to take advantage of economy because of the soil resistance, I have to perform the analysis. Then only I can claim that advantage. Otherwise, I can't claim. I do not know how much resistance will come from the soil. That's the issue. Yeah, the base shear will be matched at the ground level. Now, whole thing will be designed for dynamic analysis. Only thing is, below level will also be done for dynamic analysis. Only thing is that the scaling of the base shear will be done at the story shear in that story. Only for scaling that will be used. There is single model. I am performing dynamic analysis of the whole model. So the whole model will be designed for dynamic loads. But those dynamic loads will be scaled by a factor V. In place of BB bar by BB, it will be something like BB bar by BS, where BS is the story shear in story just above the ground. That you can do, but that will come out to be conservative. That's what I am saying. That is one way that you do dynamic analysis for the tower, design the tower by dynamic analysis, and you do static analysis of the basement, transfer the tower forces to the basement. But when you are doing static analysis for the basement, what value of SA by Z you will take? That's the issue. SA by G. Which period you will consider? You can take 2.5 on conservative side, but that may be too conservative. Now, how you can use two methods in one model? That's difficult. I am not able to understand. So if there is one model, you can do either static analysis or you can do dynamic analysis. You can do both. Part of it you can't do dynamic, and part of you, I'm not able to understand how you will do static analysis. So you are performing static analysis also, you are performing dynamic analysis also for the whole structure. For the tower portion, you are using dynamic load in combination, and here you are using static load. So when you are using static load is applied over the whole of the structure, no? Not only on basement. You have applied static load throughout. Am I right? Fine, that I agreed. One load combination you are using for basement, another. So when you are doing static analysis for whole of the structure, what period you will take? So that is not valid for basement. That period is not valid for basement. That period is valid only for tower. So you can perform dynamic analysis, or whichever analysis you do, you have to keep in mind that the period formula given in the code is valid for tower portion only. It is not valid for basement. For basement, you have to estimate period separately. Either take it conservatively 2.5, that is one option, or you do modal analysis, and from modal analysis you obtain the period. Yes. Dynamic analysis works with? No, iterative solution is there if those springs are non-linear. When we are doing equivalent linear analysis, suppose I am using non-linear springs and I want to do equivalent linear analysis, then I have to do iterations. Otherwise, those springs are like any spring or axial element. So dynamic analysis can be done with that also, with springs also.
Sir, when we are doing this multiple tower analysis,
yeah,
dynamic analysis when we perform, it will happen that one time the force is going in this direction, another time, but how can we convert that, or we should use a static forces to consider out of phase, like both buildings are going away from each other, so that diaphragm can be designed. So we have to convert those. I mean, in our office what we do, we calculate the story shears from dynamic analysis,
right.
Then we apply it on the tower in opposite direction, so and we do that analysis, or any other way.
So one method perhaps which you are saying, I will elaborate that. You mean to say is that we will perform individual tower analysis. We will scale the base shears of that individual tower analysis with the corresponding static base shear which is coming from the code. And then those scaled base shear I will apply on the model of basement. Okay, that is fine. And I will consider different possibilities.
No, sir. I'm not talking about basement. I'll do the multiple tower analysis as you...
By multiple tower analysis, you mean multiple towers along with basement together.
Yeah, together.
Yeah.
Only my concern is when the towers the forces are out of phase. Like one building is going in minus X and another building is going in positive X. So that forces when comes down, like you have shown arrow, there will be tension in the diaphragm. And for that forces, I need to design the diaphragm and maybe the beams and all.
Right.
So how that can be taken care in the analysis?
Okay. So that will not automatically come in our analysis, that those forces we have to apply statically.
Okay, so that's what I was saying. We calculate then those forces, we get the story shears.
But there is a problem even before that. When you have multiple towers and you are performing a dynamic analysis of the whole model, how to scale it with respect to the code?
That is also a problem, yes. So independently you need to calculate the scale factor, then you combine those and give those, I mean the forces can be combined. That is why ETAB has come up with multiple tower option.
I don't understand a complete model where you can model all the towers and basement together and you can scale it also with the code. I don't see any such procedure. So what I can understand is that we have to perform individual tower analysis, scale with the corresponding. So life becomes more complex when there are multiple towers. What you can do is, the issue there remains, because you will be performing separate analysis for the basement, what period of basement I should take. That you can take from the modal analysis. So you can perform a modal analysis of the structure as a whole, and whatever period is coming from there, which is where our basement is participating in the modal mass, that period you can assign SAYG for the basement, you can take corresponding to it. I don't know if somebody has really tried complete analysis of multiple towers with same basement.
Basement masses are getting excited. That still is a sort of a free vibration of the basement portion, which in practice is embedded in the ground. So it will probably underestimate the.
Agreed. It will underestimate, and it will underestimate, I should say overestimate the period.
It will overestimate the period.
Underestimate
the shear.
No. Here in this range, overestimation of the period is overestimation of shear, because the shape of the response spectrum has changed. In velocity controlled range, it was decreasing with increasing period. Here, the SAYG is increasing with the increasing period. So here, if I am overestimating the period, I am on conservative side. I am not on non-conservative side. And if we have to take soil structure interaction also into account, and then I am doing multiple towers, so it is really complex problem. I can do dynamic analysis, but then scaling with respect to the code period, that is problematic. How to do that? If the towers are of different height. Fortunately, if the towers are of same height, same type, then I will get one scale factor, perhaps I can do that. But if the towers are of different height, different shape, then it is very complex problem, how to analyze this. So we have to use our judgment. We have to identify the period of the basement. We have to calculate the scaling factors for different towers separately, and then we have to use those. Yes? Yeah. No, from the modal analysis, like we did there. So there are all zeros, and suddenly you, in a higher mode, you will get participation of the basement. You can see the mode shapes. So in this mode shape, when you will look at this mode shape, the basement will start vibrating. In earlier modes, lower modes, the basement will remain more or less static, tower only will be vibrating. Here the basement will start vibrating. Right. Yes, this period of 0.048 second, this you can use. This we have discussed. Another issue is with damping also. The damping in case of tall buildings also reduces. So there is some experimental data from ATC 72, and the damping varies between 2 to 4%, and in case of taller buildings this can be even as low as 1 to 2%. So 5% damping is really not applicable in case of tall buildings. I do not remember whether our tall building code is giving anything about damping, Vijay? No, wind analysis is different. In case of wind, the damping in any case is lower. So that is different. Even in earthquake, the damping reduces with period of the structure. So as the building is becoming taller, the period is increasing, the damping will reduce. So our code perhaps doesn't say that. ASC 7 tells that. ASC 7 suggests that we should use 2 to 3% in case of taller buildings. It should be 2% or 2 to 3%. Our code is not saying anything, so we are using 5%. Yeah, so just a small point, maybe you may be already knowing and following it. Offset between beams and columns, we were talking about the offset in case of shear wall also. So this is one of the common error which we may have. So if the beam is at an offset to the column, there will be lot of additional moment coming on the column. So that is important. Whether the column is offset with the column or the beam is offset with the column. Then modeling of the joints. So if we are modeling the beams and columns, in case of shear wall, we discussed that the width of the shear wall we will be modeling as rigid in the beam, but that is also important in case of beam column joints. The effect will not be as much as this is there in case of shear wall, but in case of beam column joints also, the joint rigidity needs to be considered. So the portion of the beam which is overlapped with the column will behave like rigid, and the portion of the column which is overlapping with the beam, that will also act as rigid. But at the same time, I told you that there are large shear deformations occurring in the joints. Due to that, there will be some deformation also. So actual problem is quite complex. The beam column joint is rigid, but at the same time it is having additional shear deformations. So for that, what ASC 41 has suggested, that we can use one of the two. Either we consider beam as rigid or as column as rigid. So that will consider the rigidity, and at the same time it will also compensate for the shear deformation, additional deformations which are occurring. So if beam is stronger than the column, we consider beam to be rigid. If the column is stronger than the beam, we consider the column to be rigid. When both are more or less same, then we consider 50%. So in ETABS and maybe in MIDAS also, we are giving a command for end rigidity. So that end rigidity factor it is asking. When we give 1, then it will make the full width of the column or beam as rigid. When we give it 0.5, it will make 50% of that length as rigid. So this can, and if we are making this error, we are not making the beams and columns rigid, our error will be on non-conservative side. We will make a flexible model of the structure, and flexible model of a structure means that we will be underestimating the SAYG value. Yeah. You are right. In new design it will not be there, but ASC 41 is actually a code for existing buildings, retrofitting of existing building. So that's why there is a possibility. In existing building, any possibility is there. It depends how they have constructed at that time. But in new building, yes, you are right. There will not be any possibility where beam is stronger than the column. Then P delta effects. So this is another issue, and most of the people I have seen in the design offices, they are making error here. So P delta effects are important. Due to P delta effect, there are additional moments occurring. We can think it like this, that at a given displacement, there will be additional moment, or at a given force, there will be additional displacement. So the effect of P delta is that it is making our structure flexible. And there are two methods to obtain that. One is what we call second order P delta analysis. So in second order P delta analysis, first we perform a first order analysis without considering P delta effects, and that whatever displacement we are getting at the story level, we calculate the equivalent additional lateral force for that and do an iterative analysis till the displacement is converged, and that will give us the value of additional displacement which is occurring, and in that process whatever additional moments are occurring in our columns, those will also be there. Then alternative approach is that we modify the stiffness matrix of the column itself. So that modification is such that it includes the axial force. So this second row and second column is modified in such a way that here this PYL is also occurring, PYL and minus PYL. So this stiffness gets reduced by PYL, and P is the axial force in this member. The catch here is that if I have to modify this stiffness, I should know the value of axial force before analysis. Okay, because I can modify the stiffness with respect to axial force, and how I will know the axial force from the analysis. So what is done? that is a common method used in ETABS or suggested in ETABS manual, that first you carry out an analysis for gravity without P delta. In gravity load, P delta effects will be very small because there is no delta, there is no sway. Usually, if the building is symmetric, there will not be sway, and even if the building is asymmetric, the sway will be very less. So you perform a P delta analysis or a nonlinear analysis. Here, when we are saying nonlinear, it doesn't mean we are considering yielding. Here we are considering only geometric nonlinearity. In geometric nonlinearity, what it does, it modifies the stiffness at each step. And when it is modifying the stiffness at each step, it is taking axial force at that step into account. So it is not giving us any yielding or any nonlinear displacement, but it will include P delta effect in the stiffness. That stiffness will be modified for the P delta effect. And then use that modified stiffness for your free vibration analysis, so that P delta effect is considered in while calculating the periods also. And it is also considered while calculating the floor loads, member forces, and story shears also in mode superposition analysis. So we do first a dummy analysis for gravity, use the stiffnesses, modified stiffnesses from there for further analysis for earthquake forces. That's another way of doing P delta analysis. In some of the software like Midas, it will be asking a load case. You have to specify a load case from where it will consider the value of P for calculating the reduced stiffness for P delta analysis. So that load case you can specify as the gravity load case. So that force it will use for calculating this modified stiffness. Both ways it can be done. So these these are available. Then there are two effects in our structures, column members. One is P capital delta and another is P small delta. P capital delta is because of the movement of one floor with respect to the other. So that is P capital delta because there is a floor movement. Then even if floors are not moving and the column is subjected to axial force and bending moment, it is deforming. So its deformation between the two end points of the column, that is small delta. So due to that also there are additional forces. So we have P capital delta as well as P small delta effect. And if we go to IS 456 or IS 800, both have these similar charts, identical charts. The effective length factors based on the stiffness, relative stiffness of beams and columns, beta 1 and beta 2. So at top and bottom, we calculate the relative stiffness, and based on that, we calculate the K factor. Most of the times, the software is asking this K factor from the user, and they are giving 1 invariably. That's wrong. So this value, actually there are two charts available. In first case, it is for what they call so-called sway frame, and another one is for no sway frame. Practically, there is nothing like no sway frame. So it's like this. If you have considered P capital delta in the analysis, you can use only no sway case. If you have not considered P capital delta analysis in your analysis, then you have to consider sway case. So sway case includes both effect P capital delta as well as P small delta. No sway case includes only P small delta. So when you have not considered P capital delta, sorry, if you are considering only P small delta, then you can see the value ranges from 0 to 1, not 0, this is, I am not able to read. From 0.5, when it is fixed case, it will be 0.5, and 1 when it is pin case. So this is for P small delta. Maximum value is 1. But P capital delta, it starts from 1 and it goes up to infinity. So depending on how much resistance is coming from the beam, this value of K can be very large. And if we are giving just value equal to 1 and thinking that we are conservative, it's not. In that case, we have to perform P delta analysis. We have to make sure that P capital delta analysis has been done by us in the software. So in ETABS, when you are designing the column, it asks, there is a clause when you are specifying the parameters for design of columns. P delta analysis done, yes or no? So if you have done P delta analysis, then you will say yes. In that case, it will use the first set of charts. If you say P delta analysis done, no, then it will use the second chart. So it will consider the P capital delta as well as P small delta at the local level. If you have done P capital delta analysis in your analysis, then you can use first set of the charts. So this option which is given, the command which is given in the software, P delta analysis done or not done, we cannot just blindly anything we press, it has a meaning. Meaning is that whether P delta analysis has been really done in the analysis forces, do they include P capital delta effect? Then
Sir?
Where?
Yes, sir.
Yeah, please.
Sir, 16700 code mentions about carrying out P delta analysis. 1893 code for buildings earlier 2016 did not mention about it. I'm not sure about the latest draft. But 1893 for industrial structures mentions about doing P delta analysis. Now my query is, generally industrial structures will not be a high-rise structures, it will be ground or G+1 structures, big warehouses. There the code specifically talks about carrying out P delta analysis. What is the relevance of it for industrial structures, whereas 1893, which is applicable for general buildings, does not talk about it?
So when IS 1893 was not talking about P delta, it was not that it was assuming that P delta effect will not occur. Okay, P delta effect will occur in any structure. Okay, in some structure it may be small, in some structure it may be very significant. So in all the structures, whether the code says or code doesn't say, we have to perform P delta analysis. If code is not saying at the moment, maybe after few revisions it will start saying that P delta analysis is to be done. So P delta analysis is to be done in any case. And it doesn't take any extra effort. We have to just press another button in the software, that's it. Actually, that sway or no sway, which is based on stability index, that is in context of gravity load. But in case of lateral load, there cannot be anything called no sway. In case of earthquake, sway will occur. So P delta effect, if this stability index is higher, okay, then the P delta effects will be relatively low. Okay, if P delta effects are low, you can use only P small delta, but P small delta will be there in any case. That you have to use even if it is no sway frame, P small delta will be there. That you have to use.
Hello, sir, here.
P delta, if you don't use P delta, the moments come quite heavy in ETAPS. So you are actually forced to use that.
But what smart people do, they will not do P delta analysis and they will click there, P delta analysis done.
Sir, as per 16700, there is a load case given here, sir. Gravity load plus or minus wind load bar earthquake. So is it mean that we have to perform different analysis for earthquake load cases and wind load cases separately for P delta with plus or minus sign, and so many analysis we have to perform? Is it practical to design for those many analysis into the...
No, there is no problem.
In the single ETAPS model, we cannot perform all these load cases, sir.
We can do. Model will be same. Only the load cases will be different. And there will be different load combinations.
Sir, actually in the definition of P delta load case, we have to define this, not in the load combination.
In P delta load case definition, what we have to define?
Gravity load plus earthquake load or wind load. Yeah, it will not work there.
Acha, you are saying that when P delta analysis is to be done, it should include the axial force due to earthquake also?
Yes.
I don't think it only means that you have to perform P delta analysis for wind also, you have to perform P delta analysis for earthquake also. It means that. So in load case you have to include P delta effects. So when you are doing earthquake or wind analysis, the P delta effect should be included there. It means that. So P delta effect, as I said, the P will come from the gravity load and delta will come from the earthquake load. Similarly, when, yes, please.
With only gravity loads, you will get one solution,
Right.
one set of results. If you perform a P delta analysis with only earthquake loads, you get another set of results in which the vertical load from the gravity loads does not exist.
No, no, no. Gravity load has to be considered in all the cases.
So you have to have one load case, primary load case, which contains the lateral load and the gravity load in one load case, one primary load case.
Right.
That becomes difficult. You can't combine them. In the sense, you can't have a load combination where the two results are superposed.
No, when we are performing earthquake load analysis, let us say using response spectrum method, okay, the P delta effects can be embedded into it. You don't need a separate analysis. As I told that in ETABS, before starting modal analysis, you should modify your stiffness corresponding to the gravity load. So before performing earthquake load analysis, you have to perform a dummy analysis for gravity, which will modify your stiffness. And that modified stiffness you will use for mode superposition analysis. So P delta effects will be considered automatically there. Same thing is done for gravity. There is one more issue, that the axial forces get modified during earthquake also. That's the issue. So I thought perhaps you are worried about that. But that doesn't come into picture because in some of the columns the axial force is increased because earthquake does not cause, when we are considering horizontal component of the earthquake, it is not causing a net vertical force. So some of the columns it is going to increase, some of the columns it is going to reduce. So net effect will be cancelled out. So that's why generally if we consider in P delta the P due to gravity alone, dead load and percentage of live load, that is good enough. Another important issue is the construction sequence analysis. In case of tall buildings, because most of you are dealing with tall buildings, so I think you have been doing it. But just to refresh, this is also very important, and it can cause lot of difference in the forces which we are getting in the beams and columns. So in case of low-rise buildings, we are assuming that the building has been constructed simultaneously. We perform the analysis for the complete building. But in case of a tall building, we have to consider how the construction proceeds. And when we are considering time-dependent effects also, creep and shrinkage, then it becomes even more important. There we have to take in construction history. And the softwares are now, all the softwares are providing the means for that. So we should consider, because the building is not constructed simultaneously. All the stories, it doesn't come into existence all of a sudden. It is gradually constructed. So the way it is constructed, same way the loads are applied and same way the loads are registered. And after construction of each story, it will be labeled. So next frame when we will be constructing, next story when we will be constructing, that will start from a labeled surface. It will not absorb the deformations which are coming from the lower stories. It will not be subjected to those deformations. So that is taken care of by this construction sequence analysis. Then last thing I want to discuss in modeling and analysis, a new check has been introduced in 16700 in the revised version, which was not there in the earlier case. So on the inter-story drift ratio, now there are two checks. One is that the inter-story drift ratio should not be more than HY 250, 0.004, that is there. And other is that to control the P delta effects, similar to the stability coefficient, which was there in IS 456 and IS 800, a new coefficient has been introduced, and it has been defined as Pi delta I Vi over Hi minus 1 R. So Pi is the axial force, sum of axial force in all the columns, delta I is the displacement, Vi is the story shear, Hi minus 1 is the story height of the lower story, and R is the response reduction factor, and the value is defined 0.2. Now if we compare it, it has been taken from ASC7. If we take ASC7, the definition in ASC7 is like this: PXY HX and VXY delta X. So there it is defined VXY delta X as the story stiffness. So it means whatever force we are applying, the corresponding displacement. So it doesn't depend on which because for a linear structure, whether we are applying dB or MC or factored or unfactored, this value will remain same. But when we introduce delta here, there is an issue that whether it is design level or it is total, including inelastic drift. So this R is extra in our code, and I understand, although code has come finally also, I pointed it out also earlier, but there is no correction, and that is the deviation. And the value of this theta in American code is also very similar. The maximum value assigned there is 0.25. So it appears that it is the same thing which has been taken. Our code they have decided as 0.2, but that R is extra. And to prove that, I will show some simple calculation. I have slightly readjusted delta I by hi. This becomes interstory drift. So interstory will be less than 0.2 Vi Pi into R. Vi over Pi is nothing but design seismic coefficient, because ratio of vertical load to the lateral load. So Vi by Pi is the design base shear coefficient. So if I take the minimum base shear coefficient, which is specified in the code for different zones, this value comes out to be like this. In zone 2, it will be 0.0014 into R. In zone 5, it will be 0.0048 into R. And if I take the value of R is equal to 5 or 6, even for the minimum base shear coefficient, this value will be quite large, about 3%. So there appears to be discrepancy, and that discrepancy is that this R should not have been there. Perhaps this R is a typographical mistake. So if we do away with this R, then the value seems to be reasonable, and it also matches with the ASC7. So I don't know whether the code is going to consider for this or not. When you are using the code, be careful. I think it should be used without R. Otherwise, this value is so high that it has no meaning. The maximum permissible drift is 0.4%, and it has been reduced now from 0.4% to 0.1% in zone 5 as per IS 1893. So if that has been reduced, applying a limit of 3% does not make any sense, because it should have been smaller than that. Then it will make a sense. If it is much larger than this drift limit, this doesn't make sense, and the reason appears to be that this value of R has been added erroneously. Okay. So that's all. These are the changes. I cover changes as well as some important concepts which were already there in 16700, but we might have missed those. So that I cover for 16700. Any question up to this point we can take up. Yeah.
Be ignored in lateral load resistance in all seismic zones. These shall be designed as a gravity elements for deformation conformity. Can we explain this?
Sorry, can you read from the first line? Which clause you are talking about?
This is tall building code 7.3 11. Stiffness of frames with flat slab as horizontal members. That is
frames with flat slab.
Yeah.
Okay.
That is slab column frames.
Slab column frame. Yeah.
Shall be ignored in lateral load resistance in all seismic zones. These shall be designed as gravity elements for deformation compatibility.
Right. So it means that the flat slab cannot resist lateral load. Flat slab should not be used to resist lateral load. So
previously you told some slab has to is the media for transferring the
transferring, but not resisting. So it will be checked even when you are using flat slab and it is combining shear walls, then it will be checked for that. But it cannot be used to resist. The slab column frame, you will be considering the column strip of the slab, and then you are designing it as an equivalent frame. So for lateral load, that is not to be done. It will not be designed for lateral load. It can't resist lateral load.
So only columns you have to check for?
Not column or slab, nothing. Shear wall, which you are providing, either shear wall you have to provide, or you have to provide a brace frame, or you have to provide a perimeter frame. So shear walls and perimeter frame only will take lateral load. So shear wall and perimeter frame will be designed for 100% earthquake force.
Correct, but he's telling again these shall be designed as gravity elements for deformation component. Means he's telling internal columns has to be deformation component. R is equal to 1 factor.
Right.
Correct.
Right. So slab and columns will be designed, but those will be designed with R is equal to 1, like we design our gravity elements.
Okay. So one more thing, sir. In the tall building code in the 8.6 class, flat slab structural wall system he has mentioned.
Sorry?
In the
Flat slab?
Structural wall system in the same tall building code, 8.6 class.
Okay.
So in this he is mentioned in structures with flat slab system as gravity load carrying system, structural walls shall carry all the lateral loads of the building and column strips of the flat slab shall not be included in the lateral loading system.
Right.
So he is again confusing.
No. It only means that it will not be, its contribution will not be considered while designing shear wall. So you can make two models. If you want to do that, you can make two models. In one model, you will pin the top and bottom of the columns. Okay. Then flat slab will not come into picture in lateral load resistance. Okay. Design it. Next one you make where the pin is removed, okay, and R is equal to 1.
Okay.
In that case, you design your flat slab and column.
Okay. This is per flat slab system, building system.
Yeah.
Okay.
Sir.
So for this 2016 code, clause 7.10.4, 2% RCC structural wall plan density. It has mentioned 2%.
Right.
So that seems quite high.
You are lucky, sir. Here it is mentioned only 2%. If you look at the NDMA guidelines for hospital buildings, it is mentioned 4% in each direction.
So is it feasible?
No.
So what do we do about it? You don't follow this clause.
If you can't provide it,
But in
the code cannot be followed.
residential you can achieve it, but commercial it is problem.
Residential also it is very difficult to achieve 2%. I mean, if I would not have tried myself, I would have said, what is there? You do it. If I try myself, then only I will understand that how difficult, I mean, what really 2% means. So recently we have tried to design some hospitals. All the walls in the hospital we have made RCC. Okay. Even then we could not achieve 2%.
It is plinth area, total plinth area.
Yeah.
By, walls area.
You try. Okay. You try and send me some examples.
Okay.
Sir, today we will not have tea break.
Okay.
Because ZTI has, with some administrative difficulty, they have booked the auditorium for next program at 5:30.
Okay, so we have to finish by 5:30.
We can have maximum 5 to 10 minutes. 6
Okay.
The other program people have only come outside. So we will not have tea break. We will have tea break after.
Okay. So you mean 5 to 10 minutes from now or 5 to 10 minutes from 5:30?
5:30.
5:30. So we can go up to 5:30, 5:40. Okay, okay, good.
Sir.
Sir.
Drift check should
Okay.
drift check should it be done for SLS combinations or ULS combinations?
Lot of confusion. Again, previously, if we talk about the existing code, IS 1893 was saying unfactored load. That was very clear. 16700 says design forces, design load. Now, design load to me means factored load. If I compare with ASC 7, our code is giving limits more than what ASC 7 is giving. And ASC 7 is giving for the total. There is no ambiguity. They are giving it very clearly, multiplying by CD. So they are giving 1% to 3%. So if I compare that, this should have been on factored load, on design load. But now the code says very clearly that it is on serviceability load. So lot of confusion in this. I think that has been written by mistake that it is serviceability load. The type of limits they have specified, those should be applicable at the design load, not at the serviceability load. If they were giving smaller limits, I can agree that those are applicable to serviceability earthquake. But the limits which have been given are at par, or rather larger than what have been specified in Eurocode and American code for design earthquake level. Sorry? We can achieve. Only thing is you have to make your sizes of beams and columns larger. That I agree. 0.1% is too stringent.
Yeah, for that design load is very difficult. Design.
That I agree. So I'm not talking about that flat slab. We are talking in general.
General. Okay.
Hello.
Flat slab, as I told you, that 0.1% was decided so that the people are discouraged to use flat slabs.
So actually,
So
then SLS I can achieve it.
Then on the lighter note, people started using PT slabs.
Yes, sir. Hello.
Yes.
Sir, I have got one question regarding maximum slenderness ratio. You know, many times we end up in a building which are rectangular. We have core which is little deeper, but at the edges as we go, the width is very small compared to what core is. So how should we calculate? Like we started calculating on weighted average something like we calculate average width, taking area divided by the length and all. So is there anything by which we can confirm what length or how we should, because it fits in drift, deflection, everything, but we are restricted with this clause because it says 8.
Actually, the clauses should not be in terms of these parameters, because you can't interpret these in technical terms. You can interpret these in legal way, and then you start fitting these also in some legal way. And we being technical person, we can't discuss that, because if there is a technical solution, we can. If there is a legal solution, how can we find out? So that type of clause, I do not have much respect for those type of clauses. As long as you are satisfying all the technical requirements, your structure is having drift within limit, the overturning at the foundation is avoided, and if there is an overturning, it should be properly designed with the piles. It should be within the safe uplift capacity of the piles. If all that is being followed, you are considering all the consequences. If there is a liquefaction, then what will happen to the uplift capacity, all that, if you are taking into account. I don't see this type of requirements have any meaning, that the slenderness has to be within this limit, and you can't use this system in this.
Okay. And second question was pertaining to NDMA code. Like we were designing hospitals.
It's not NDMA code, it is NDMA guidelines.
NDMA guidelines, okay,
Yes.
not code.
Yeah.
But then I think that is mandatory for hospitals. Like
Not mandatory,
not
fortunately.
okay. Because 4% is impossible
Impossible.
to achieve.
I mean, I couldn't go more than 2%.
No, we also tried. We put almost like 450, 500 thick wall, 600 thick wall all around, but still with the area we could, still
We can't.
maybe 2% we could reach.
We
But
can't.
in that there is the clause like there we don't use Z by 2, we use
Right.
directly Z
Right.
plus importance factor of 1.5
Right.
and then load factor of 1.5. So with
That
new
is okay. I agree with that. That I can defend.
yeah, but with new code, because where we are going to use for hospitals, I think there then we don't need to use that, right? Even if we want to use some of the clauses of NDMA, we don't want to use that.
I mean, the new code is more or less at par with NDMA guidelines, because now we will be designing for MCA.
Okay.
So now new code says that the hospital buildings will be designed for MCA. Sorry, depth of foundation. Right. Natural ground level. Yeah.
Hello, sir.
Yeah.
Sir, can you go to slide around 58? There is one diagram of compression and tension regarding backstay effect.
'58.
58, somewhere around 58. that beam we provide additional reinforcement for near to this one. One second, third one, like 55.
55.
Yeah.
Okay.
Yeah, this right side diagram I could not understand.
Okay. So this right side diagram is showing that some shear force, some force will be transmitted to the direct shear, some force will be transferred through compression here, and some force will be transferred through tension here. So we can calculate how much will be the shear force being transmitted, and then what is the compression capacity of this composite section, and what is the tension capacity of this composite section. We will sum those three, and that should be more than the force which is being transmitted to the shear wall at that floor level.
Shear wall is between only between point B and C, right?
Right.
So what is that component?
So that's what is shown here, that part of the shear force will be transferred from the slab to this reinforcement, this strut. So this, because suppose it was, the shear wall was outside the slab, then it will be transferring only through shear. Now I have embedded shear wall into the slab. So what will happen? The part of the slab will act in compression and part of slab will act in tension. That will also, by directly thrusting the shear wall, it will transfer the force.
So when we say shear wall, are you considering between A to D, or is it actually B, between B?
Shear wall is between B to C only.
Then when you are saying it is contributing or taking load from A and
So
B,
you think two cases. In one case, shear wall is outside the slab, and another case, the shear wall is inside the slab. So there will be a difference in the two cases.
Hello.
Yeah.
So I have like three doubts. First one is regarding the concept of modifiers.
Okay.
So like for ULS we are making the building more flexible, and SLS we are making it little stiffer and computing the parameters. So in SLS though we are underestimating the deflection, and in ULS we are making it more flexible and reducing the force. So what is the like concept behind this modifiers?
See, concept behind these modifiers is that during earthquake loading, or for that matter under any loading, whether it is earthquake or any other loading, the concrete is going to crack.
Yeah, that is fine. But why is there a difference between
Amount of cracking will be different. Amount of cracking will depend upon the magnitude of load. Under higher load, the cracking will be more. So the effective stiffness will be less.
Okay.
Under lower load level, serviceability level, it will be more or less uncracked. Not uncracked, it will be more or less elastic. So the cracking is going to be less.
Okay, got
so
it.
there the stiffness will be higher.
Okay. So in code, like the second question is in code they are saying for drift calculation, so shall not exceed 0.004 times the story height under action of design based shear. So drift there.
Where in which code you are reading from?
IS 1893.
Old one or the new?
It's old one.
Old one, yes.
So basically, as per this old one, they are asking us to calculate the drift based on the ULS model.
Right.
If I am not wrong.
Right.
Because they are mentioning design based shear.
Right.
In the same clause below, displacement estimates obtained from dynamic analysis method shall not be scaled. So
scaled means these need not to be scaled for BB bar by BB correction.
Yeah. Then in that case, for deflection, from which model should we calculate? So
without scaled? I mean before doing BB bar by dynamic
model,
analysis?
In ULS model or SLS model for displacement?
ULS.
Okay, that is also
ULS without BB bar by BB correction.
Okay. So one more thing is like, for example, in while discussing the shear wall, that biaxial bending concept, you were saying on the major direction, most probably the biaxial curvature won't happen. But what about the minor direction of the shear?
Sorry, biaxial will not happen on the, yes, okay. Right. So deformed shape will be different. Yes, you are right. On the
minor axis of the shear.
Minor axis, there can be what we call double curvature bending.
So still it is a shear wall. Only we are checking.
Yeah.
Okay.
Because its primary action is in the major axis direction, not about the minor axis.
Okay. One more last question. For example, if there is a flat slab system with periphery columns, so the code is saying like that 25% to be considered in the design of the columns, right? Force to be taken by the columns. But in the analysis model, if we are finding the column is not contributing to the 25%. So if it is not contributing, should we scale up that and make it 25% or shall we ignore that?
Because no. There are two. Suppose you have made a model and your column participation in the total base shear comes out to be less than 25%. So you have two options. Either you compromise with response reduction factor of 4 and design whatever forces are coming in any element. That is one option. Other one is you want to use response reduction factor of 5, which is for dual system. In that case, the columns will be, although those are not taking 25%, in your analysis, you will design them for 25%.
But in my case, it is a flat slab system. Its response reduction factor is 3.
No, flat slab is fine, but flat slab is not registering lateral load. In flat slab also, the lateral load is registered by the shear wall and the perimeter frame. Sorry? 3 in case of flat slab, yes, you are right.
So in that particular case, what we will do? Flat slab?
No, in case of flat slab, sorry, I misunderstood that. In case of flat slab, the columns are to be designed for 25%. The perimeter frame is to be designed for 25% in any case.
Even though if it doesn't carry
whatever it is taking, that is immaterial. It will be designed for 25%, designed to carry 25%.
So why is that concern for the flat slab system alone?
Sorry?
Why is there a concern for that flat slab system alone, I am asking?
Because we want to discourage you using flat slab. Because that was on lighter side. The flat slabs are prone to punching shear failure. So punching shear failure depends on the drift and the shear capacity consumed by gravity. Because there is punching shear due to gravity load also, and there will be additional punching shear when it will be deforming. So there is a drift limit. ACI 318 provides a chart where you can determine the drift which you can permit, and that is the total drift. It is not the design level drift, the total drift which you can permit. So 0.1 drift is minimum there. If your punching shear capacity or punching shear demand is almost equal to its punching shear capacity, then also you can permit up to 0.1% drift. So that value of 0.1 has been taken in our code.
Hello, sir. Hello, sir.
Sorry? Right. When you are designing shear walls and the columns, the flat slab columns will be pinned.
That periphery, including periphery?
Periphery are not flat slab. Those are beam column frame.
Okay. Only internal, okay.
Internal columns where you are not providing beams. Those columns which are not connected by beams on any of the two directions. If you connect those columns in one direction also with beam, you can consider it. Yeah, please.
Hello, sir. मेरा क्वेश्चन कपलिंग बीम को लेकर के है.
ओके.
अगर मेरा कपलिंग बीम में L/D का रेशियो 1 है और 1 से लेस है.
हाँ.
और उसमें मैं केवल लॉन्गिट्यूडनल रेनफोर्समेंट प्रोवाइड करता हूँ और शियर प्रोवाइड करता हूँ. मैं इन एनी केस में डायगोनल प्रोवाइड नहीं कर रहा हूँ. तो क्या मैं फेलियर की तरफ जा रहा हूँ या मैं सेफ हूँ?
फेलियर की तरफ आप जा रहे हैं. देखिए, अर्थक्वेक में फेलियर तो होना ही होना है.
ओके.
क्वेश्चन सिर्फ ये है कि आपका फेलियर डक्टाइल होगा या ब्रिटल होगा. तो आपके केस में कंक्रीट ट्रस एनालॉजी में कंक्रीट विल फेल. योर टाउ एवरेज इज गोइंग टू एक्सीड, टाउ वी इज गोइंग टू एक्सीड टाउ सी मैक्स. सो इट विल बी द फेलियर ऑफ कंक्रीट इन शियर, which will be brittle failure. So you will have a brittle failure.
Okay. If I use capacity shear in that case, then I am safe.
If you are using capacity shear.
Capacity shear, yes.
But how you can have? If you could have used capacity shear, then L/D cannot be less than 1. Or in other words, if L/D is less than 1, it is impossible to design for capacity shear.
Okay. Means what you are saying that if L/D is less than 2, then we should go for like diagonal reinforcement only.
Diagonal reinforcement.
Is like
Then you can avoid brittle failure.
okay. Even if I am doing capacity set, then also there is no meaning.
No, you can't do it. That's the problem. If you could have done it, then this issue would not have come, because it is not possible to satisfy capacity shear because the depth is too large. Moment capacity, even with nominal reinforcement in moment, will be so large that this section cannot sustain that much shear force.
Okay, sir. There is a limit at tau VE. If that is more than 0.1 under root FCK multiplied by LS by D, then I need to go for like diagonal reinforcement.
Right,
only.
right.
Where this is coming from actually?
From
What is the
experiments.
principle behind
From experiments. So they have done experiments, and from experiments they have seen that up to what level the concrete can resist the shear stress.
Okay, because that limit is coming to be very low actually. It's like 4 ratio of M25 grade and L by D is equal to 1. I am at 0.5 Newton per mm square only.
So it is from experiments.
Okay. Thank you, sir.
Hello.
Yeah.
My question is related to coupling beams only.
Okay.
In code it is written that diagonal reinforcement to be provided to resist both moment and shear.
Right.
But in the equation to calculate the diagonal reinforcement, they have considered only shear.
Right.
So how to calculate, or how we should
it will be automatically satisfied, you can check. So the moment which can develop, moment and shear have a relationship. Okay, in a beam, the moment is, if you calculate moment on both sides, so 2m will be equal to V into L. So there is a relationship between moment and shear force. You satisfy any one of the two, the other will be automatically satisfied. So that relationship is given in terms of V, but it will also satisfy moment, because there is a relationship between moment and shear which can generate.
But we have checked for few beams, the moment criteria is not getting satisfied.
It will.
So
We can check, because the component, this inclined diagonal reinforcement, this will have component in horizontal and vertical direction. Horizontal component will take care of the moment, the vertical component will take care of the shear. And the ratio of the two will depend upon L by D. And the relationship between moment and shear will also depend on L by D. So that's why it will satisfy.
Another question, for tall buildings, for 2 meter length beams are also formed in coupling action. So if it has 700 mm depth, after reducing all the cover, stirrup, dia and bottom reinforcement dia, the angle we are getting hardly 15 to 20 degree for the diagonal reinforcement. So whether it will be effective in resisting shear, or what should be the ideal angle of that diagonal reinforcement?
That is not in your hand. That will depend upon L by D of the beam. So whatever range the code is specifying, L by D range it is specifying for diagonal beam, in that range you can use it. You can't use it outside this. So that angle you can't decide. You can't decide that my L by D is, let us say length is 2 meter and there is some depth. I will provide diagonal reinforcement at a higher angle. You can't. The diagonal reinforcement will be provided along the diagonal, and the angle of the diagonal will be decided by L by D. So this is not your choice.
Sir, in case of tall building, the kind of foundation, is it only raft or pile raft, or individual footing also can be adopted?
I don't know whether individual footing you will be able to design in some case.
Yes, sir. In case of say SBC of 200.
Okay, so if it is on rock.
Yes, sir.
Okay.
So now, can isolated footing can be designed, or we have to necessarily go for a raft foundation?
See, if you are using a shear wall, and in case of a tall building you will be using a shear wall. So what happens in case of shear wall? Due to its stiffness, it gets lot of moment at the base, and that moment needs to be counterbalanced at the foundation, otherwise there will be uplifting at the foundation. And if uplifting is occurring at the foundation level of the shear wall, its moment capacity will not develop. So it will not be possible to design, even if it is rock, it will not be possible to design foundation of a shear wall as an isolated footing. At least combined footing is true. Rock anchors theoretically yes, but there are two issues with rock anchors. One is its capacity, because rock is very unreliable material. So how to get the capacity? That's estimation of the capacity. Second is durability. If with time, with corrosion, there is no cover, water gets into it, corrosion occurs. So durability is another issue, because we have explored this not in case of buildings, but in case of some bridge foundations. So there we are having isolated footing and uplift is occurring. So to take care of that uplift, can we go for that? So it was explored with railways, and finally there were issues related to durability. So whether it will survive 50 years or not, that is questionable.
Sir, generally in case of shear wall, it will be combined footing, core wall in the central area.
So if you are having combined footing for the shear wall, so that it is counterbalanced by the column forces, and other columns you are having isolated footing and it is connected by tie beams, I think you can use that.
Okay.
Sorry? I don't know if there is any clause in the code which says that you have to use raft only. I don't think there is.
That's what is the confusion, sir.
Huh?
Now, modeling of soil, so while modeling the raft foundation through spring constant or modulus of subgrade reaction, zoned spring constant or zoned modulus of subgrade reaction shall be utilized for design. So does it imply that it has to be necessarily pile foundation or pile raft, or isolated footing can be designed?
No, in this case it has to be raft or piled raft.
So no isolated footing is allowed?
In case of soil, yeah. But in case of rock you can use. Shall I use? You can zoned spring constant for isolated footing. But in rock, why you need to consider flexibility? So, no, code has clearly written for soil. Code is writing for soil, not for rock.
हेलो सर, अच्छा मैं मेरे क्वेश्चन को थोड़ा फिर से एक बार रिइटरेट करता हूँ
बोलिए।
कपलिंग बीम वाले के लिए।
जी।
आपका ऐसा बोलना था कि वो कंक्रीट क्रश हो जाएगा, करेक्ट? लाइक बिफोर इट विल रीच टू द सर्टेन वैल्यू ऑफ टॉ वी ई, करेक्ट? बट मेरा ऐसा कहना है कि कंक्रीट तब क्रश होगा जब वो टॉसी मैक्स को क्रॉस करेगा। तो वी कैन गो अप टू टॉसी मैक्स विद द लॉन्गिट्यूडनल शियर एनफोर्समेंट। जब वो मेरा क्रशिंग के पास है, देन आई शुड गो फॉर लाइक diagonal reinforcement kind of thing. Is it a correct like a statement or say it is?
It is correct, but estimating shear stresses in the coupling beam, that is a complex thing.
Okay.
So tau C max value you are saying that is okay.
Yes.
But how to obtain tau V? We are using simplified calculation. So estimating tau V will be complex. That's why to simplify that, based on the experiment, that value has been given based on the gross value of the shear force divided by cross sectional area. Okay. Like actual distribution of the shear stress is going to be different. It is not going to be uniform.
That means like in some case that can be bypassed.
What can be bypassed?
In some of the cases, if I need to provide longitudinal shear enforcement only, then this tau v wala limit 0.1 under root FCK LS by D, can that be bypassed?
No, I don't know. How can it be bypassed?
Again, I will come for the same question that our concrete is going to crush when there will be like tau C max limit. Before that, it will not going to crush.
Okay. So, but you have to calculate your tau V accurately. How you are going to calculate your tau V? That's the question.
Okay, that will
here we are assuming a uniform distribution of stress. Actual stress is varying within the section.
Okay.
So, we have to calculate the actual variation of the stress, which is complex.
Okay. Does any other code have this certain kind of limit?
Yes, ACI 318, all the codes have this. The limits may be slightly different, but there are limits in all the codes.
Okay, sir. Thank you.
In 167023, It says the load combination for initial analysis considering P delta effects shall be taken as 1.2 DL plus 0.5 LL plus or minus 1.5 EL slash WL. I don't understand this.
So perhaps they mean to say is that the axial force which you need to consider for P delta analysis, because for P delta analysis you need axial force. So that axial force can be calculated for this combination.
Yeah, but traditionally P delta analysis was done with service loads, never with factored loads.
No. It is to be done with factored load. Yeah. Only thing is, I mean, in case of earthquake. So 1.5. So because P delta effects we are doing for strength design, not for serviceability design. I have another doubt there. Actually, I'm sharing my doubt. The displacement during earthquake will be more than what we are calculating. So actually, it should be more. So doing P delta analysis, because this type of P delta analysis is not allowed in other codes. There are different methods of doing P delta analysis when I was looking at ASC 7, because actual delta will be R times what we are considering here. So these additional moments which I am considering in this analysis, even as per these so-called factored load, it will be much less than what actually is going to occur in my structure, which will be displaced. So it should be P into R delta analysis, not P delta analysis. It should be PR delta analysis in our case. It has to converge. It converges even when we do nonlinear analysis. There we consider full delta. It converges. So there is no problem of convergence. This P delta, when we do, I mean, our friend was pointing out, that is correct, that if we use two ways of designing, either we use sway case factors from the code, or we do P delta analysis ourselves plus no sway case. The reinforcement in the first case is much larger. And I was bothering that why it is so. Because in that case, in no sway case, when these P delta effects are calculated, they are considering the yield curvature at yield. And that's perhaps the reason that in our case, it is when we are doing P delta analysis, in our analysis, the moments are coming out to be much less. The reason for that may be this, that we are doing it for reduced load, not for the actual load. So actually, and interestingly, yes, in the new code it will be taken care of, because in new code, analysis will be done for elastic force. And then while designing, it will be divided by R. In the earlier code, the analysis was done for the load reduced by R. Now the analysis will be done for the full load, and while designing, we will divide it by R. So there perhaps it will be taken care of. Yeah. I mean, don't do P delta analysis, just use the second chart.
So
yeah, please. Microphone ले लीजिए.
Sir.
Yeah.
Sir, here.
अच्छा हाँ बोलिए.
Sir, there is one clause in 16700 9.6. Expansion joints should be preferably be avoided in a basements for a tall building.
Right.
So if provided, such joints shall be detailed for a water tightness.
Right.
This comes under a foundation clause, list of a foundation. So what the code is trying to guide us for this?
No, I couldn't get foundation. What are you saying regarding foundation? The first part is okay.
Yeah.
That expansion joint should be avoided, and if provided, water tightness should be ensured.
Yes.
So I don't see any problem with this. Do you have any problem with this part?
Code is telling to provide a grade slab or something which is being means it is giving a focus on connection between a raft and a non-tower area or something. It is something.
No, it is talking about the slabs, not about the foundation. Slab in the basement. Foundation in any case will be monolithic. Only the slabs, there the expansion joint will come. Whenever we are providing expansion joint without basement also, expansion joint does not go into the foundation. Foundation need not to be separated, because the foundation temperature does not change.
Sir, clause number 9, it is a foundation. This is a clause number 9.6. So, as I understand, it comes under its focus
Now,
on
what
the
does the
foundation.
clause actually read?
Yeah.
Can you read it out?
Expansion joints shall preferably be avoided in a basements for a tall buildings. Full stop. If provided, such drawings shall be
Right.
suitably
So it
detailed
is
for water
talking
drainage.
about basement slabs, not about raft. In raft, we never provide an expansion joint.
Okay.
In foundation, no expansion joint is necessary. Not only necessary, it is not to be provided.
So, sir, the point is, code is giving more emphasis on a backstay and all that procedure, which is basically not cleared, and we are not able to do
You remember when Professor
Yeah.
Gadgil was presenting the backstay effect, he told that earlier we used to provide expansion joints. We used to separate the tower from the rest of the basement. It was making the designer's life simple. But there are so many other problems associated with that, particularly the water tightness. So many problems were there that now we don't go for that. And what we were expecting, that due to temperature movement, a lot of stresses will develop, nothing like that happened. So now the thinking is that let's keep whatever is inside the ground. Okay, the temperature is not going to increase much, the variation is not going to occur much. Let's keep it monolithic, not provide expansion joint. That will create more problems.
सर वो जो आप कह रहे थे ना पी डेल्टा जब करते हैं तो उसमें रीइंफोर्समेंट काम आता है, उसका मेन रीज़न ये है कि ई टैब्स में ऑटोमेटिकली इफेक्टिव लेंथ 1 लेता है, तो उस वजह से इफेक्टिव लेंथ जैसी 1 लेता है तो उसमें रीइंफोर्समेंट कम दिखाता है, जबकि हम अगर पी डेल्टा नहीं करते तो रीइंफोर्समेंट ज़्यादा की तरफ जाता है। और जो आप कह रहे हैं पी डेल्टा का, वो पी डेल्टा में जब आप लास्ट डिफॉर्मेशन वाला केस लेंगे ना तब एक्स्ट्रा रीइंफोर्समेंट और मोमेंट आएगा, उसकी वजह से आपका ज़्यादा सरिया आएगा। वो उसके केस अलग हैं, नॉन लीनियरिटी में केस डिफाइंड है जिसको हम यूज़ नहीं करते, हम सिर्फ पी डेल्टा का ऑप्शन इधर यूज़ करते हैं। उधर आप अगर ज्योमेट्रिक नॉन लीनियरिटी को कंसिडर करेंगे, उसमें 3 ऑप्शन है, जब आप उसको लेंगे तो आपका मोमेंट बढ़ता है पी डेल्टा की वजह से।
तो आपका कहना ये है कि हम जब लार्ज डिफॉर्मेशन एनालिसिस करते हैं तब मोमेंट ज़्यादा आता है कॉलम में, और जब खाली पी डेल्टा लेते हैं तो मोमेंट कम आता है।
वो एक्चुअल पी डेल्टा वो है जो लास्ट डिफॉर्मेशन के साथ है।
अच्छा, दिस नीड टू बी सीन। मीडास वाले भाई साहब, आप कुछ बता सकते हैं इसमें? लार्ज डिस्प्लेसमेंट एनालिसिस वर्सेस पी डेल्टा एनालिसिस, व्हाट इज द डिफरेंस? हाँ, ओके, I also need to see, I mean, I will also look into it, that what difference it makes when you do large displacement analysis and
Yes,
P
sir.
delta analysis.
I have checked it, sir. What he's saying is correct.
Okay,
Yeah.
where?
I'm saying, sir, what he's saying is correct, sir. I've
So
checked it.
when you are using the large displacement option, it is giving larger moments,
Yes.
and when you are using simply P delta option, then it is determining less moment. Okay.
What moment should come? Yeah, that is.
Sorry?
That's the moment.
Bending moment in the columns.
Yeah, whatever should come, it's not lesser, but yeah, when you use big delta, it gives you higher moments. Yes.
No, I am confused again. We are comparing here two options in ETABS. One is P delta and another is large displacement analysis.
Yes, large displacement analysis.
So which one are both giving same moment?
No, large displacement analysis gives higher moments.
Higher moments. Okay, so that's what we wanted to confirm.
Sir, in last
So preset P delta is one way, and there is the second way. You don't define preset P delta, you define the P capital delta in the non-linear geometric nonlinearity load cases, convert the linear into geometric nonlinearity, the answer comes the same for either.
No, here in nonlinear, I have seen those options. In nonlinear analysis, there are 3 options. One of those is P delta, one of those is large geometry analysis and large displacement analysis, and there is one more. So there are 3 options. So what he is talking about is P delta and large displacement analysis. So what is the difference between these 2 methods? I am not very clear.
No,
that what exactly the software is doing.
Small p delta, if you take predefined, you don't have to define P capital delta.
No, P small delta no software can take. P small delta is to be taken into account at the design stage only.
Yeah.
Because if you want to model P delta in the software, you have to subdivide your column into a smaller number of elements. Dividing, if you are modeling column with one element, P small delta, no software is taking care of.
I mean, what is the option given is preset P delta. In that P small delta is given in ETABS. So that is one way to take care of geometric nonlinearity by previous definition. Second is you give all load cases, convert it into P capital delta nonlinear cases. You can compare because ETABS also has given the same video in their display model. Both are getting the same answer.
So I have not looked into those, so we have to look into it. Or somebody from EDAS or ETABS clarifies that, then we can understand those.
ETABS have given the free video on their website on this.
We have to look into it.
Hello.
Where?
Sir.
Yeah.
Yeah. See, it was about modifiers, the question. Slab modifiers which you give in ULS, it is 0.25. Of course, it is from American code also. But don't you think it is a little on a higher side because we should give it, I mean, slab should be cracked more because what we have seen when you have got shear walls in major direction and if it is connected by even 150 thick wall, as you go higher, then it comes into framing action comes in and we are not detailing that slab as ductile, we are not making it ductile, so it is bound to crack. So in earlier before few years when 16700 was not there, in ETABS we used to give slabs as membrane, so it is not taking out of plane bending. Now with this 0.25 what is happening is I feel, it's my personal feeling, that we are under designing shear walls because that framing action in major direction with shear wall happens in the slab case, and those slabs we are not designing.
The slab, whether you are, even if you consider the full stiffness modifier equal to 1, I don't think it can cause any significant bending in the major direction of the shear wall.
Sir, it does.
It does that?
Yes, I have done a frame where I gave just a 2 meter by 150 thick slab for say 20 storied or 25 storied. And if I compared the cantilever shear walls with that slab, the deflection and axial forces start coming in.
It will have impact, sir.
It has a big impact. So
impact.
Yes. All the time I'll share if I get email.
Yeah, so it may be in the third category of Professor Gardigal's lecture, the foolish impression. So it may be, so maybe it needs to be done.
So in Delhi what we have started doing, we convince our clients that we should give modifier as 0.1 instead of 0.25, at least in ULS. In service it's fine when wind load is there, but in earthquake we started giving it 0.1 and we actually...
Yeah, so you have to keep your mind and brain open always, and there will be always the things which will not be covered by the code and lectures, and so nothing can replace the designer.
Okay,
so
I just wanted your opinion on this. Like,
I have not thought. I have to yet to see that how much I was under this false impression that the slab is not making any significant impact on the bending moment in the shear wall.
Bending moment shown in the beam also less.
No, that I understand. Because in that case, the slab starts transferring the moments directly. That I understand that the beam moments are modified, but the shear wall moments are also modified.
Not overall it impacts. Local, some walls it also has impact. We also check that.
I think they have to go in plane shear in the slab. They have to give 1, I think. Only bending they have to give 0.25. F1 and F22 they have to give 1, I think.
Right. So axial, the in plane is axial.
Then it will not have impact.
But only the concern here is...
No.
Sir, only the concern...
He is also talking about out of plane only. He is not talking about in plane. Membrane, when we are using it, is full membrane.
But the only concern is like, which my opinion is like, what he's saying is correct. 0.25 we don't do the ductile detailing of the slab. But my one more opinion is that even slab has a stiffness. Ignoring 100% is looks like a way we are going over design, because slab itself practically has a stiffness.
No, he is not ignoring. He is rather saying that we should increase it. We should take higher. He is not asking to reduce it. In place of 0.2, he is suggesting 0.25. 0.25. So he is suggesting to increase it. Am I right?
To reduce it, 0.1.
0.1
he said.
0.1 in flexure.
Yeah. More flexible, more cracking.
Its effect is less. Total effect is 0.
The reason what for the asking is we don't do the ductile detailing of the slabs.
So you are saying when we are taking 0.1 and when we are taking 0.2, there is a significant effect in the bending moment in shear wall. So, I mean, what benefit you are drawing when you are reducing it from 0.2 to 0.1? Okay, so you mean you are on conservative side? Okay.
Sir,
Even sir, in that same thing, I want
No,
to.
but he is not asking you to do it. It is his method, his own method, a conservative
No,
method.
sir,
So let him
I
do.
have-
You go ahead with your method.
No, here, sir, opinion the same thing. See,
Yeah.
there are two opinions. First, if you have a 0.25 slab as a modifier, in that case, slab, the walls show some lesser forces because slab itself has some stiffness. But the concern is we don't do slab as a ductile detailing. Okay, when we say lateral force, we need to have separately the slabs 0.25 means some force is taken by the slab. We need to design, we need to detail, which we don't do as for ductile detailing. And the second, so in that case, we feel like when the earthquake will come,
No, no, no. So what you want? You want him not to use 0.1?
we the
So
same.
why we are debating?
want your opinion.
अरे आगे चलते हैं यार ऐसे तो
need a opinion.
बहुत सारे difference of opinion होगा. So we need not to debate on if everything. I agreed. As long as he is going on conservative side, I said okay, welcome, go ahead.
Even sir, one more little drift. In
Yeah.
1893, we have a modifier of ULS and we have a interstory drift we check for unscaled. In the tall building, there are two modifiers given. One is for serviceability, one is for the strength model. Now, what happened is many of the consultants, what they do now, tall building, so they check the unscaled drift only, but in the serviceability modifier. So, what is your opinion in that again? Whether that's a correct?
I mean, first of all, in case of earthquake, I feel that the limits which are given in the code should be checked at the design level earthquake, not at the serviceability level earthquake. Okay. And when we are doing a design level earthquake, we should follow the corresponding modifiers.
Okay.
Sir, in share wall design yesterday you discussed the effective length factor you have to take 0.8 when taking while checking the share design. Length of
Okay,
the
so
length of
shear
the wall,
length, effective shear length is 0.8 LW.
yes.
Yeah.
But in USA code it takes a full length. What is the difference? ACI code takes full length of the wall, not 0.8.
I do not know. I think there also it is 0.8.
They are giving strength reduction factor, the pi value.
No, no. Strength reduction factor is different. The purpose of strength reduction factor is like our partial material factor of safety. But length they are taking, I think they are also taking 0.8 LW.
Gross area they are telling.
Huh?
The gross area they are telling. 8 times.
Gross area
lambda, yeah.
they are taking. I have to check.
Sir, for coupling beam, for calculation of diagonal reinforcement, code says the shear force from the earthquake case alone. Is it from the earthquake load case alone or it is from the combination? There is an ambiguity. So now while calculating diagonal reinforcement, VU value. So whether it is from earthquake case alone or it is from the combination.
You mean we should consider whether we consider gravity load there or not?
Yes, sir.
So I think it should be total shear force, but I have to check. I have not given attention to this language which you are saying that code is saying earthquake load case alone.
Yes, sir.
So
and abbreviation is given.
if code is saying earthquake load case alone, then
VE, say abbreviation is given tau VE. So everybody is interpreting it's only from earthquake.
Earthquake,
case.
yeah.
Load case only, not from the combination.
Yeah, if code is so clear, it has given tau VE also, so then it is earthquake case alone.
Case alone. Yes, thank you, sir.
I'm sorry, I have not given attention to that. I will look into it after going from here. So should we talk a little about, no, there is no time now left. So any other question or we close here? Maybe base isolation sometime next? Online? Okay. So base isolation we can have online. So one afternoon, one evening, we will have an online session on base isolation.
Sir,
Yeah.
sir, that aluminium farm or construction we are doing nowadays for tall buildings.
My one.
Yes, sir. Any other code available for that, sir?
No.
Because that
I have not seen any code on that. I am also looking for. In fact, I wanted to start one PhD thesis on that, one PhD student. But the problem is that no test results are available on that system. So I wanted to do some numerical work, but to calibrate my numerical model, I need experimental results. So experimental results are not there, and I have to first do the experimental testing. And experimental testing is very costly. I need project for that. So I'm looking for funding so that I get some money. I start testing first, and then I will go for numerical work.
Thank you, sir.
Okay, so thank you very much. So nice. I was so happy.